There's something both humbling and exhilarating about looking up at a clear night sky. For thousands of years, humans have gazed into that profound darkness, tracing constellations, telling stories, and trying to make sense of our place within it all. Yet every answer we've found only seems to unveil deeper mysteries, pulling us further into the unknown. We've mapped planets, stars, and galaxies. We've even caught gravitational ripples from black holes colliding billions of light years away. And still, the greatest question remains: what lies at the very edge of the universe? What happens where space itself seems to end? This is not just a question for scientists in observatories or philosophers in quiet rooms. This is something that speaks to the very core of human curiosity. We are drawn to boundaries. We are pulled toward horizons. And there is no greater horizon than the cosmic one, the place where known physics blurs into speculation, where light may not even travel, and where the rules of reality as we understand them might completely break down. It's here, in this uncharted territory, that some of the most breathtaking mysteries of our time are waiting. In this video, we're setting out on a journey to explore 30 of the most compelling, puzzling, and awe-inspiring mysteries about the edge of the universe. From dark energy's relentless push to the possibility of parallel worlds, from cosmic voids that defy explanation to the mind-bending idea that our universe may be just one bubble in an infinite multiverse, we'll venture into concepts that challenge not only what we know, but how we think. This isn't just a tour of theories. It's an invitation to wonder, to imagine, and to stand at the frontier of human understanding, looking out into the deepest unknowns. So let's begin. Our journey begins with the very first and perhaps most fundamental mystery, the limit of our own view. We often hear that the universe is 13.8 billion years old, a number etched into the very foundation of modern cosmology. So it seems logical to assume that the farthest thing we could possibly see is 13.8 billion light years away. The distance light has had to travel since the dawn of time. But that intuition is wrong. In reality, our cosmic horizon stretches out to an astonishing 46.5 billion light years in every direction. This discrepancy isn't an error in measurement. It's a profound clue about the true nature of the cosmos. The key to unraveling this puzzle is one word: expansion. The universe isn't static. It's stretching, growing, increasing the distance between galaxies that aren't already gravitationally bound. Think of it like baking raisin bread. As the dough rises, every raisin moves away from every other raisin. Now, imagine a photon of light, emitted from a raisin representing one of the first galaxies, beginning its journey across the expanding dough toward our raisin, which is us. The space between us and that photon is stretching even as the photon moves toward us. The photon is fighting a constant headwind, its journey taking far longer and covering a far greater effective distance than it would in a static universe. By the time that ancient light finally reaches our telescopes, the galaxy that emitted it is now much farther away than the mere travel time of the light would suggest. That current, vast distance to those most remote observable objects is the 46.5 billion light-year figure. It marks our cosmic horizon, the ultimate boundary of observation. This creates a haunting reality. There are regions of the universe from which light, even traveling at the ultimate speed limit, has simply not had enough time to reach us yet because the space between has expanded too much. Those regions are forever beyond our view, hidden behind what cosmologists call the particle horizon. It's a horizon not unlike the one we see on Earth. We can't see what lies beyond the curve because light travels in straight lines. But this cosmic horizon is made of time and expanding space, not water and land. We have no idea what structures, what galaxies, or what entirely different configurations of matter might exist beyond that veil. The universe we can see may be just a small island of the known in an ocean of the unknowable. And this horizon isn't static. It's actually growing as more light has time to arrive. But the relentless acceleration of the universe's expansion means that distant galaxies are eventually rushing away so fast that their light will never reach us. They will fade from view, forever lost to the void, making our observable universe not only limited but also slowly shrinking in terms of its total content. This horizon is the first and most tangible edge we encounter, a border defined not by a physical wall, but by the fundamental laws of physics and the history of everything. But if the cosmic horizon is the ultimate limit of what we can see, that immediately begs an even bigger question. What lies beyond it? Is there simply more universe, more galaxies and stars stretching on forever? Or does the nature of reality itself change past that point? This is one of the most speculative and profound puzzles in all of cosmology, and theories range from the mind-bending to the almost philosophical. One compelling idea is that the universe is indeed uniform, a concept known as the cosmological principle. This suggests that on the largest scales, the distribution of matter and energy is roughly the same everywhere. If this holds true beyond our horizon, then what lies beyond is simply more of what we see here. More galactic superclusters, more filamentary structures woven into the cosmic web, stretching on indefinitely. In this view, our observable universe is just one patch in an impossibly vast, perhaps even infinite, whole. The edge isn't a true edge at all, it's just the limit of our vision. However, the inflationary theory that so successfully explains the universe's early moments introduces a far more radical possibility. Inflation proposes that a fraction of a second after the Big Bang, space-time underwent a period of exponential, faster-than-light expansion. Crucially, most models suggest that this inflation didn't happen everywhere at once and then stop. Instead, it may be an eternal process, ongoing in some regions while ending in others. Where inflation ends, a hot, dense, expanding universe like our own bubbles into existence. But beyond our horizon, inflation could still be happening, continually giving birth to an endless multitude of other bubble universes, each with its own unique properties. This is the basis of the multiverse concept. In this staggering scenario, what lies beyond our horizon isn't just more stars, but entire other universes, potentially with completely different fundamental constants and laws of physics. The strength of gravity, the mass of an electron, even the number of spatial dimensions could be different in these other bubbles. Our universe, with its specific laws that allow for galaxies, planets, and life, would be just one rare outcome in an infinite cosmic landscape of possibilities. This leads to a deeply philosophical challenge. If these other realms operate under different physical laws, and no information can ever cross the horizon to reach us, can we even call them part of our same universe? The word universe traditionally meant all that exists. The multiverse idea forces us to reconsider that definition, suggesting all that exists is far grander and more diverse than we ever imagined. Some physicists argue that without any possibility of observation or interaction, the question of what lies beyond is not a scientific one but a metaphysical one. Science, they say, is built on testable predictions and falsifiable claims. If something is forever hidden behind a causal horizon, can it ever be more than a fascinating idea? Yet others counter that the theory of inflation, which gives rise to the multiverse concept, does make testable predictions about what we can see within our own bubble, like the specific pattern of fluctuations in the cosmic microwave background. In this way, the shadow of what lies beyond is imprinted on the universe we can observe. Ultimately, the mystery of what lies beyond the horizon forces us to confront the very limits of scientific inquiry. It asks whether everything that is real must be observable, or if the cosmos is filled with wonders that are, by their very nature, forever out of reach. It challenges us to expand our definition of reality itself. But if the observable universe is just our local neighborhood, and the vast beyond may be filled with infinite possibilities. That naturally leads us to a more fundamental question about the entire cosmic fabric. What is the actual shape of the universe? This isn't about the shape of galaxies or clusters, but the overall geometry of space, time itself on the grandest possible scale. Is the cosmos flat like an endless sheet of paper, closed like the surface of a sphere, or open like a saddle, curving away in every direction forever? The answer to this deceptively simple question holds the key to the universe's ultimate fate, its total size, and even whether it is finite or infinite. For a long time, this was a question for philosophers. But today, we have a powerful tool to measure the shape of the cosmos, a fossilized echo from its infancy known as the cosmic microwave background. This faint glow is the remnant heat from the Big Bang, and it is incredibly uniform, with tiny temperature fluctuations that are like a baby picture of the universe's density. The apparent size of these fluctuations on the sky acts as a cosmic ruler. Think of it like this: the geometry of space acts as a lens, either magnifying or minifying the apparent scale of these patterns. In a flat universe, the paths of light rays are straight, so we see these ancient ripples at their true scale. A spherical universe would act like a magnifying glass, making the fluctuations appear larger than they should be, while a hyperbolic, saddle-shaped universe would make them appear smaller. The incredibly precise data from satellites like Planck has measured these fluctuations, and so far, all the evidence points overwhelmingly towards a flat geometry. The measurements align almost perfectly with the predictions for a flat universe, with any deviation falling within a tiny margin of error. This is a profound result. A flat universe has mind-boggling implications, the most significant being that it is almost certainly infinite. Just as a flat piece of paper can extend forever in 2 dimensions, a flat universe could extend without bound in all 3 dimensions. This means that beyond our particle horizon, space doesn't loop back on itself or end. It just continues, filled with perhaps an endless repetition of galactic superclusters, stars, and even planets. The total number of galaxies, of stars, of atoms would be literally infinite. But we must consider the other possibilities, as the margin of error, however small, still exists. What if the universe is actually spherical? In this geometry, the universe would be finite but without any boundary, much like the surface of a ball. If you could travel in one direction for long enough in a closed universe, you would eventually return to your starting point from the opposite direction, without ever encountering a wall or an edge. The fate of a spherical universe is ultimately a dramatic one, a big crunch. The positive curvature would mean that the density of matter and energy is high enough that the expansion will eventually halt, reverse, and pull all of reality back down into a singularity. The third, more exotic possibility is a hyperbolic or open universe, shaped like a saddle or a Pringle. This geometry would indicate a density so low that gravity's pull could never rein in the expansion. In this scenario, the universe would not only be infinite, but its expansion would accelerate forever, leading to the loneliest possible fate, a big freeze or heat death, where everything is pulled so far apart that the cosmos becomes a cold, dark, and empty void. Each geometry paints a completely different portrait of our cosmic home and its final chapter. The fact that our best measurements point to flatness suggests we live in a universe that is perfectly balanced on a knife's edge, destined to expand forever into an infinite emptiness, a conclusion that is as awe-inspiring as it is humbling. Knowing the shape of our universe, flat and infinite, doesn't just tell us about its vast size, it points us toward its ultimate fate. The geometry and the destiny of the cosmos are deeply intertwined, governed by a mysterious force that we are only beginning to understand. So what does the future hold, not for our planet or our sun, but for reality itself trillions upon trillions of years from now? The answer depends almost entirely on the true nature of dark energy, and scientists have proposed several dramatic and frankly haunting finales. The leading theory, and the one most supported by current observations, is known as the heat death, or the Big Freeze. In this scenario, the accelerated expansion driven by dark energy continues unchecked forever. Galaxies beyond our local group will eventually be pushed away so fast that their light can no longer reach us, leaving our night sky increasingly empty. Within each galaxy, stars will slowly burn through their fuel. Suns will flicker out, one by one, leaving behind cold stellar remnants like white dwarfs and neutron stars. Over almost unimaginable timescales, even these remnants will decay through proton decay, and supermassive black holes will slowly evaporate away via Hawking radiation. The universe will approach a state of maximum entropy, where energy is evenly distributed throughout space. There will be no more temperature differences, no more energy gradients to drive any process, no stars, no planets, and certainly no life. It will be a cold, dark, and utterly empty void, a static equilibrium that lasts for eternity. This is not a dramatic explosion, but a slow, quiet whisper into an infinite silence. But what if dark energy isn't constant? What if it gets stronger over time? This possibility gives rise to a far more violent and immediate end, the Big Rip. If the repulsive force of dark energy increases and eventually overcomes all other forces in the universe, the expansion wouldn't just separate galaxies, it would tear apart everything. First, galaxy clusters would be shredded, then individual galaxies themselves would be pulled apart. As the force grows stronger, it would overcome the gravitational hold of solar systems. Stars would be ripped from their orbits. In the final moments, the force would exceed the electromagnetic forces holding planets and stars together, and they would be vaporized. Ultimately, just a fraction of a second before the end, the expansion would become so powerful that it would overcome the nuclear forces holding atoms themselves together. Every molecule, every atom, every proton and neutron in the universe would be torn asunder. The fabric of spacetime itself would be shredded. The universe would end not with a whimper, but with a catastrophic, instantaneous unraveling of reality itself. There is, however, a more cyclical alternative to these cold and violent ends, the Big Crunch. This was a popular theory before the discovery of the universe's accelerating expansion. It suggests that if the density of matter and energy in the universe were high enough, the collective pull of gravity would eventually slow the expansion to a halt, reverse it, and begin pulling everything back together. Galaxies would start rushing toward each other. The background temperature of the universe would rise, and the sky would glow hotter and brighter. Eventually, all matter and energy would be compressed back into an infinitesimally small, hot, dense singularity, a mirror image of the Big Bang. This scenario offers a kind of cosmic symmetry, a closed loop of creation and destruction. While current evidence for dark energy makes this seem unlikely, some theories speculate that dark energy could decay over time, potentially allowing gravity to once again take the lead and pull the universe back in on itself. This idea of a cyclical universe naturally leads to the most speculative yet fascinating possibility, the Big Bounce. If a Big Crunch occurs, what happens next? The bounce theory proposes that the universe doesn't just end in a singularity, it rebounds. The collapse into an ultra-dense state triggers a new Big Bang, birthing a new universe from the ashes of the old. This process could, in theory, repeat forever, an eternal cycle of expansion and contraction. Each new universe might inherit some properties from the one before, or it could be completely reset with different physical constants and laws. This idea is compelling because it avoids a true absolute beginning or end, offering a potentially infinite timeline for existence. While highly theoretical and not supported by mainstream evidence, it represents a profound shift in how we view cosmic history, not as a linear story with a definitive start and finish, but as a potentially endless cycle of renewal. The evidence that will ultimately determine our fate is written in the behavior of dark energy, represented by its equation of state parameter. If this value is exactly -1, the heat death is our destiny. If it is less than -1, the Big Rip awaits. Our ongoing mission, through telescopes like the James Webb and future observatories, is to measure the properties of dark energy and dark matter with ever-increasing precision, to read the cosmic handwriting that will tell us which of these incredible stories is our own. While we can chart the universe's grand geometry and theorize about its ultimate fate, one of the most immediate and personal cosmic mysteries is unfolding right in our own galactic backyard, pulling us toward an unseen destination. For decades, astronomers have known that our Milky Way galaxy is not adrift in a static sea. It's moving, and it's moving fast. Along with the entire local group of galaxies, we are racing through space at a staggering 600 kilometers per second. That's over 2 million kilometers per hour. But this motion isn't random. It's a trajectory, and it points directly toward a specific, hidden patch of sky near the constellation Centaurus. Something with an immense gravitational pull is drawing us in. This is the mystery of the Great Attractor. The intrigue of this mystery is magnified by a frustrating obstacle: we can't see it. The direction of this pull lies squarely behind the plane of our own Milky Way, a region astronomers call the zone of avoidance. Here, thick clouds of interstellar gas and dust block almost all visible light from the universe beyond. It's like trying to peer through a dense cosmic fog bank. For a long time, this zone represented a massive blind spot in our maps of the cosmos, a perfect hiding place for a gravitational monster. So, what could possibly be massive enough to pull millions of galaxies, including our own, toward it? Early theories proposed a single, enormous concentration of mass, perhaps a supercluster of galaxies, or even a massive, unseen structure that defied conventional understanding. The quest to unveil this hidden attractor required new eyes telescopes that could see not in visible light, but in wavelengths that slice through the dust. Radio, infrared, and X-ray telescopes began to pierce the veil, and what they revealed was both an answer and a new, deeper mystery. They didn't find one single great attractor, but rather something even larger. The pull we feel appears to be the combined gravitational influence of an entire complex of massive structures, a gravitational tapestry woven across hundreds of millions of light years. At the heart of this lies the Norma cluster, a dense gathering of galaxies, but that is merely the nearest anchor point. Behind it stretches the mind-boggling Laniakea supercluster. Laniakea, which means immeasurable heaven in Hawaiian, is our home supercluster. It's a vast cosmic filament, a river of galaxies a staggering 500 million light-years across, containing the mass of over 100,000 Milky Ways. Our local group, the Virgo cluster, and many other groups are all like tributaries, flowing down the gravitational slopes of this immense structure toward its dense center, the gravitational basin we call the Great Attractor region. So, the force pulling us is not a single point, but the collective draw of an entire continent of galaxies. Yet, the story doesn't end there. Our entire Laniakea supercluster, with its Great Attractor, is itself in motion, being pulled towards something even more colossal. This points to an even larger gravitational anomaly, often called the Shapley attractor or the Shapley concentration, the largest known concentration of matter in the observable universe. It's a staggering collection of dozens of massive galaxy clusters, a gravitational beacon so powerful it is tugging on superclusters themselves. This reveals a universe of hierarchies within hierarchies, where what we once thought was the ultimate source of a pull is merely a waypoint in a far grander cosmic flow. The Great Attractor is no longer the final destination, but a signpost on an infinite journey, reminding us that even when we solve one mystery, it often just leads us to a deeper, more profound one waiting in the shadows. This growing discrepancy is more than just a small statistical glitch. It's a crack in the foundation of modern cosmology, and it's known as the Hubble Tension. At its heart, this mystery is about one of the most fundamental numbers in all of science, the Hubble constant, which measures the current rate of the universe's expansion. For decades, astronomers have been refining this number, expecting that different methods would eventually converge on a single, agreed-upon value. Instead, the opposite has happened. The two most powerful and respected methods for measuring this rate are now giving us two different, irreconcilable answers. It's as if you used two different rulers to measure the same table and got two different results, and you're absolutely certain both rulers were correct. This isn't just a minor puzzle. It threatens to upend our understanding of the universe's history, composition, and ultimate fate. So how do we even measure something as vast as the expansion of the universe? The first method, often called the early universe or physics route, uses the cosmic microwave background. Satellites like Planck have mapped this ancient afterglow from the Big Bang with incredible precision. By studying the subtle patterns of hot and cold spots in this radiation, cosmologists can calculate the ingredients of the early universe, the amounts of normal matter, and dark energy, and then run the cosmic film forward using our well-tested model of physics to predict what the expansion rate should be today. This method is incredibly robust and gives us a Hubble constant value of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec, which is a distance of about 3.26 million light-years, a galaxy is moving away from us at 67.4 kilometers per second faster. The second method, the late universe, or distance ladder approach, builds a chain of measurements to gauge distances to faraway galaxies directly. It starts with precise parallax measurements to nearby stars, which then calibrate the brightness of pulsating stars called Cepheids variables. These Cepheids, whose pulse rate is directly tied to their true brightness, are then used to measure distances to galaxies that contain both Cepheids and a specific type of supernova explosion, called a Type Ia supernova. These supernovae are crucial because they are standard candles. They all explode with nearly the same peak brightness, making them brilliant beacons for measuring vast intergalactic distances. By observing how fast these supernova host galaxies are receding from us, astronomers get a direct, empirical measurement of the current expansion rate. This painstaking work, led by teams like the one using the Hubble Space Telescope, consistently gives a higher value, about 73 kilometers per second per megaparsec. The gap between 67 and 73 might seem small, but in the world of high-precision cosmology, it's a chasm. The error bars on each measurement have shrunk so much due to better data that they no longer overlap. The probability that this discrepancy is just a fluke has now become astronomically small. This leaves scientists with two deeply unsettling possibilities. Either there is a hidden, systematic error in one of the measurements that we haven't been able to find despite over a decade of trying, or our standard model of cosmology is incomplete. We might be missing a piece of physics. If the error is not in our measurements, then the implications are profound. It would mean that the universe we see today doesn't quite match the universe that evolved from the conditions we see in the cosmic microwave background. Perhaps dark energy isn't a constant cosmological constant as we've assumed, but an evolving force that has changed strength over time. Maybe dark matter has some strange, unexpected properties that we haven't accounted for. There could even be a previously unknown type of neutrino or another form of relativistic energy in the early universe that subtly altered its evolution. Some theorists have even proposed more exotic ideas, like a early dark energy that briefly surged during the universe's first few 100,000 years, tweaking the initial conditions just enough to resolve the tension. Each of these potential solutions would represent a monumental shift in our understanding of physics. This is why the Hubble tension is so captivating. It's a genuine, unresolved mystery at the frontier of science. It's not a debate over semantics. It's a direct challenge to our most successful model of the cosmos. Major observatories, including the James Webb Space Telescope, are now turning their gaze to this problem, aiming to scrutinize the cosmic distance ladder with unprecedented clarity to rule out any lingering observational errors. The resolution of this tension, whether it reveals a flaw in our measurements or new physics, will undoubtedly be a Nobel Prize-winning discovery. It represents a rare and exciting moment where the universe seems to be trying to tell us something we don't yet understand, a cosmic secret waiting to be decoded. And as we grapple with the Hubble tension, trying to reconcile the universe's past with its present, we are forced to confront the enigmatic engine behind this accelerating expansion: dark energy. This is perhaps the single greatest mystery in all of modern cosmology. We can measure its overwhelming effect. It constitutes about 68% of the entire energy density of the cosmos, yet we have no idea what it actually is. It's the dominant force shaping the destiny of everything, and it remains a complete enigma. The story of its discovery is a classic tale of scientific surprise. In the late 1990s, two independent teams of astronomers were using distant Type Ia supernova to measure how much the universe's expansion was slowing down due to gravity. To their astonishment, they found the opposite. The most distant supernova were dimmer than expected, meaning they were farther away than our models predicted. The expansion wasn't slowing down, it was speeding up. Some mysterious repulsive force was stretching the very fabric of space-time itself, overcoming the gravitational pull of all the matter in the universe. This revelation was so shocking, it earned the researchers the Nobel Prize and completely rewrote the textbook story of cosmic evolution. So what could this force be? The leading candidate, and the simplest one, is the cosmological constant, an idea first proposed by Albert Einstein and later called his greatest blunder. This concept suggests that empty space is not nothing. It has a fundamental energy density, a constant pressure inherent to the vacuum itself. According to quantum physics, virtual particles constantly flicker in and out of existence in this vacuum, and this seething quantum foam could generate a repulsive force. If this is true, dark energy is just a property of space. As the universe expands and more space is created, more dark energy comes into being, leading to a runaway acceleration that continues forever. This model fits our observations well, but it has a colossal problem. When physicists try to calculate the theoretical value of this vacuum energy, their answer is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of physics. This enormous discrepancy has led scientists to consider more dynamic possibilities. Perhaps dark energy isn't a constant but an evolving field, similar to the inflatoned field that drove the universe's exponential growth in its first moments. This concept is often called quintessence. Imagine a fifth fundamental force that permeates all of space but whose strength can change over time. It could be weakening, which would mean the acceleration might eventually slow or even reverse. Or it could be strengthening, making the acceleration even more violent and potentially leading to that catastrophic Big Rip scenario. The appeal of quintessence is that it could potentially resolve the Hubble tension by allowing the expansion rate to evolve in a way that our standard model doesn't account for. There is a third, even more radical possibility: that dark energy doesn't exist at all. What if we are misinterpreting the data because our understanding of gravity itself is wrong? Einstein's theory of general relativity has been spectacularly successful on scales from our solar system to the entire observable universe. But what if it breaks down on the largest imaginable scales? This idea, known as modified gravity, suggests that we don't need a mysterious dark energy component. We just need a new theory of gravity that naturally explains the accelerated expansion without it. These theories are incredibly difficult to formulate, as any new model must perfectly replicate all the successes of general relativity on smaller scales, while only altering its behavior across cosmic distances. It's a monumental challenge, but one that a number of physicists are pursuing, as it would represent a true revolution in our comprehension of the fundamental forces. Understanding the true nature of dark energy is not merely an academic exercise. It is absolutely crucial for predicting the ultimate fate of everything that exists. Is our universe destined for a cold, lonely heat death, a violent big rip, or something else entirely we haven't even conceived of? Major projects like the Dark Energy Survey and the future Vera-C. Rubin Observatory are mapping the universe in unprecedented detail, measuring the growth of large-scale structure and the history of expansion across billions of years. They are trying to catch dark energy in the act, to see if its strength has changed over cosmic time. The answer will tell us not just what dark energy is, but how the story of our universe will finally end. But if dark energy is the mysterious force pushing the cosmos apart, then dark matter is its shadowy counterpart, the hidden scaffolding that pulls the universe together. We've come to understand that the majestic galaxies and vast clusters we see are just the visible tip of a much deeper cosmic iceberg, embedded in enormous, invisible halos of dark matter. This mysterious substance, which does not emit, absorb, or reflect light, reveals its presence only through its immense gravitational pull, guiding the motion of stars within galaxies and entire galaxies within clusters. For the most part, our models assume that dark matter behaves in a simple, predictable way. It clumps together under gravity and provides the gravitational anchor around which luminous matter can coalesce. But when we venture out to the most extreme environments in the universe, to the sparse cosmic voids and the outermost fringes of galaxy clusters, we have to ask, does dark matter always play by the same rules, or could it act differently in these frontier regions? This question is at the heart of some of the most detailed and ambitious computer simulations ever run, projects with names like Illustris and Millennium. These virtual universes are born from equations and initial conditions that mirror our best understanding of the Big Bang. Researchers seed them with dark matter particles and let the laws of physics play out over billions of simulated years. The results are breathtakingly complex cosmic webs, intricate structures of dark matter filaments connecting dense nodes where galaxy clusters reside, all surrounding vast, empty bubbles known as cosmic voids. In these simulations, dark matter forms incredibly smooth and massive halos around galaxies, halos that extend far beyond the visible starlight. The behavior of dark matter in these outer halos and filaments is critical. It's the gravitational skeleton that dictates how the entire cosmic structure forms and evolves. However, a troubling puzzle has emerged when we compare these sleek simulations to our real-world observations. When astronomers measure how mass is distributed in real galaxy clusters, often by studying how the cluster's gravity bends the light from more distant galaxies, an effect called gravitational lensing, they sometimes find a discrepancy. The dark matter in the inner regions of clusters seems to behave as expected, but out in the sparse outskirts, the distribution can appear noticeably clumpier and less smooth than the simulations predict. It's as if the virtual dark matter is too well behaved, too efficient at settling into a serene, predictable halo, while the real stuff out on the frontier is a bit more messy and disordered. This isn't a universal finding, but it's persistent enough to make cosmologists wonder if they're missing a piece of the puzzle. This opens the door to a fascinating possibility. What if dark matter isn't entirely dark? What if it can interact with itself through forces other than gravity? The standard model assumes it is cold and collisionless, meaning the particles move relatively slowly and simply pass through each other and normal matter without a trace. But if dark matter particles could occasionally bump into each other, even very weakly, it could explain the clumpiness we see. These self-interactions could transfer energy, smoothing out the densest central parts of a halo while scattering material and creating a fluffier, more extended distribution in the outer regions. It's a subtle effect, but in the extreme low-density environments at the edge of a cluster's influence, even a tiny interaction cross-section could have a significant impact on how dark matter organizes itself. The emptiest places in the universe, the cosmic voids, present an even greater challenge. These are the deserts of the cosmos, regions hundreds of millions of light-years across that contain very few galaxies and seemingly very little matter. In simulations, dark matter filaments are still predicted to thread through these voids, a faint web of invisible structure. But if dark matter has any unique properties, any strange behaviors, these ultra-low-density environments are where they would be most pronounced. It's the difference between studying the properties of water in a rushing river versus studying a single molecule of water vapor floating in a vast, empty room. The rules might be the same, but the context is so extreme that any minor effect becomes magnified. Some theorists propose that the core of the issue might not be with dark matter itself, but with our understanding of gravity. Modified Newtonian dynamics, or MND, suggests that gravity behaves differently at extremely low accelerations, like those found in the outer reaches of galaxies and in voids. While MND has had some success explaining rotation curves of individual galaxies without dark matter, it struggles to account for the full range of evidence for dark matter on the scale of galaxy clusters. However, its existence highlights the profound nature of the mystery. When we see something acting strangely at the edge, we must question whether it's the particle we don't understand or the fundamental force itself. The distribution of dark matter in these frontier zones is more than a technical detail. It's a crucial test for our most fundamental theories of what makes up the cosmos and how it holds itself together. When we tally up all the ordinary matter in the universe, the stars, the galaxies, the gas clouds we can see, we come up dramatically short. This is the missing baryon problem, and it's a deeply embarrassing one for astronomy. We're not even talking about the mysterious dark matter or dark energy here. This is about the normal stuff, the protons and neutrons that make up everything we can see and touch. Based on the incredibly precise measurements of the cosmic microwave background and our understanding of Big Bang nucleosynthesis, the recipe for the early universe, we know exactly how much of this baryonic matter should be out there. Yet, when we add up all the visible stars, the dust in galaxies, and the cool gas we can detect, we've only found about half of what the models insist must exist. It's as if we've taken a cosmic census and half the population has simply vanished without a trace. So where did it all go? The leading theory suggests this missing matter isn't hidden in some exotic form, but is instead hiding in plain sight, spread so thin and heated so dramatically that it has become nearly invisible to our telescopes. This is the warm, hot intergalactic medium, or WIM. Imagine the vast, empty spaces between galaxies and galaxy clusters. We used to think these cosmic voids were truly empty, but we now believe they are threaded with a faint, ultra-diffuse web of gas. This isn't the cool, dense gas that forms stars. This is gas that has been superheated to temperatures between 100,000 and 10 million degrees Kelvin by the immense gravitational forces and shock waves generated as the cosmic web formed. Gas at these extreme temperatures doesn't emit light in the visible spectrum we can easily see. Instead, it glows faintly in high-energy X-rays, or it absorbs specific wavelengths of light from even more distant, brilliant objects like quasars. Finding this tenuous fog is one of the most difficult challenges in modern observational astronomy. It requires incredibly sensitive X-ray telescopes and a bit of luck. The primary method is to look for the subtle fingerprints this gas leaves on the light passing through it. When the intense beam of light from a distant quasar travels billions of light-years to reach us, it passes through these filaments of WIM. Atoms within the hot gas, like highly ionized oxygen and nitrogen, will absorb very specific wavelengths of that quasar's light. By analyzing the quasar's spectrums, splitting its light into a rainbow of wavelengths, astronomers can search for these tiny, telltale dips in intensity, the absorption lines that act as a signature for the whim. It's painstaking work, like trying to identify a specific type of fog by the precise pattern of how it dims a faraway street lamp. Some of this missing matter might also be hiding in a slightly more obvious, yet still elusive, place: the enormous halos of hot gas that surround entire galaxies and galaxy clusters. Our own Milky Way, for example, is believed to be enveloped in a massive corona of gas reaching temperatures of millions of degrees. This gas is too hot to collapse into the galactic disk to form stars, but it is a significant reservoir of mass. For larger structures, like the vast Perseus galaxy cluster, the intracluster medium, the superheated plasma that fills the space between the galaxies, contains far more normal matter than all the stars in the cluster's galaxies combined. While we can detect this plasma with X-ray observatories because it is dense enough to glow, accurately weighing it all across the universe to account for the full missing half is an immense logistical challenge. The resolution to this mystery is critical because it speaks to the completeness of our cosmic inventory. If we can't even find all the normal matter predicted by our most fundamental models, how can we be confident about the more exotic components like dark matter? The hunt for these missing baryons is a colossal effort that involves cross-referencing data from telescopes across the electromagnetic spectrum, from ultraviolet to X-ray. New missions, like the X-RISM Observatory, are specifically designed to have the high-resolution, spectroscopic vision needed to finally track down these last hidden reservoirs of ordinary matter, confirming that the universe hasn't lost anything, but has simply been keeping its secrets in the hardest-to-see places. Imagine that after mapping the entire sky in incredible detail, you discovered that the oldest and most fundamental map of reality seemed to be subtly aligned with your own hometown. This isn't science fiction. It's the startling puzzle known as the axis of evil, a name chosen by cosmologists with a sense of dramatic irony to highlight how deeply unsettling this finding truly is. At the heart of this mystery is the cosmic microwave background, that pristine snapshot of the infant universe. According to our most cherished cosmological principle, this radiation should be essentially uniform in all directions. The tiny fluctuations in temperature, those seeds of future galaxies, should be randomly and evenly distributed across the sky, with no preferred direction or special axis. This assumption of uniformity is the bedrock of modern cosmology. The axis of evil suggests there might be a crack in that foundation. The anomaly was first spotted in the data from the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed with even greater precision by the Planck satellite. When scientists analyzed the pattern of hot and cold spots in the cosmic microwave background, they found something that defied easy explanation. The largest-scale fluctuations, the biggest waves in the fabric of the early universe, appeared to be aligned along a specific axis, and that axis seems to be eerily correlated with the plane of our own solar system, and even the direction of the sun's motion through the galaxy. It's as if the universe's grandest blueprint has a faint arrow pointing back at us, a suggestion that our location might not be entirely random after all, which directly contradicts the cosmological principle's assertion that there are no special places in the universe. The scientific community has responded to this with a mixture of intense curiosity and deep skepticism. The most obvious and conservative explanation is that this is a colossal fluke, a statistical anomaly that will disappear with more precise data or better analysis. After all, when you're dealing with a map of the entire sky, it's always possible to find some pattern that looks significant purely by chance if you look hard enough, a phenomenon often called look elsewhere bias. Another strong possibility is that it's not a feature of the universe itself, but an artifact of our own observation. Perhaps there is some unknown, subtle contamination in the data, maybe from our own galaxy's foreground emissions that weren't perfectly subtracted out, inadvertently imprinting a local signature onto this global map. Yet, if the alignment proves to be real and not an illusion, the implications are staggering. It could mean that the universe has a preferred direction on the largest scales, a fundamental anisotropy that we have yet to understand. This would force a radical rewrite of our standard model of cosmology. Some theorists have proposed that this axis could be a fossil relic from the era of inflation, a direction imprinted by the mysterious field that drove the universe's initial exponential expansion. Even more speculatively, it could be a hint of something that existed before the Big Bang, a structure or a boundary condition that set a preferred direction for the birth of our cosmos. Others have ventured that it might be evidence of our universe brushing up against another in a vast multiverse, an interaction that left a directional scar on the CMB. The name, Axis of Evil, perfectly captures the dilemma it presents. If it's real, it undermines a core principle of science. If it's an error, it's a persistent and embarrassing one that has survived two of the most sophisticated space missions ever launched. Resolving this mystery is a primary goal for future observatories, which will measure the cosmic microwave background with even greater sensitivity, desperately searching for any systematic error, or finally confirming that the universe has a preferred direction, a cosmic north that points directly back at our humble address in the cosmos. But as we try to peer through the cosmic fog of our own galaxy to understand the Great Attractor, we are forced to ask an even larger question about the structure of the cosmos itself. Is the universe, on its very largest scales, fundamentally smooth and featureless, or does it contain structures of such immense size that they challenge our most basic assumptions about reality? This is the mystery known as the end of greatness, and it probes the very validity of the cosmological principle, the idea that the universe is homogeneous and isotropic when viewed at a sufficiently large scale, with no special locations or directions. For a long time, astronomers believed that while the universe is clumpy on the scale of galaxies and even clusters, this clumpiness would eventually smooth out. Once you zoomed out far enough, you would see a uniform, almost boring sea of matter. This was the predicted end of greatness, the scale at which the cosmos stops organizing itself into discernible structures and becomes a truly random distribution. Observations seem to support this. The cosmic microwave background is incredibly uniform, and galaxy surveys showed that the distribution of galaxies became smoother as they looked at larger and larger volumes of space. It appeared the cosmological principle was safe. Then we began to find the giants. With ever more powerful telescopes and sophisticated sky surveys, astronomers started to map the universe in 3 dimensions, plotting the positions of millions of galaxies. What they found was a cosmic web of stunning complexity, with galaxies strung along vast filaments that connect at dense nodes, surrounding enormous, empty voids. And some of these structures were not just large, they were staggeringly, almost improbably, huge. The most famous and controversial of these is the Hercules Corona Borealis Great Wall. This is not a physical wall but a gigantic filament, a conga line of galaxies that stretches for an estimated 10 billion light-years across the sky. To put that in perspective, that's roughly 1/10 the diameter of the entire observable universe. The mere existence of such a structure is deeply puzzling. According to our models of the universe's evolution, there hasn't been enough time since the Big Bang for gravity to pull matter together over such an immense scale. It's like finding a single sandcastle on a beach that's a mile wide and a mile high. The known processes of wind and water simply couldn't have built it. The Hercules Corona Borealis Great Wall is not alone. We've found other colossal structures like the Sloan Great Wall, the South Pole Wall, and the Laniakea supercluster that we are a part of, which itself is 500 million light-years across. Each new discovery pushes the boundary of what we thought was possible, making us question where, or if, the end of greatness actually occurs. If structures this large exist, it suggests that the universe might not become smooth and homogeneous on any scale we can observe. There might always be a larger filament, a more immense void, a greater wall just beyond our current field of view. This presents a serious challenge to the cosmological principle. If the universe is supposed to look the same everywhere, finding these massive irregularities is like discovering that the texture of a sheet of sandpaper changes dramatically depending on which square inch you're looking at. It forces cosmologists into a difficult position. Either our standard model of the universe's formation and growth is missing a key ingredient, or we have to accept that the cosmological principle only truly applies on scales so vast they are beyond our current observational reach, meaning the end of greatness does exist, but at a scale even larger than these walls. Some scientists even argue that these enormous structures might be optical illusions, artifacts of the way we measure distances and map the cosmos, though this is becoming harder to maintain as evidence accumulates. The implications are profound. If the universe isn't homogeneous, it means our location might not be typical after all. Our calculations about the total amount of matter and energy, and even the very fate of the cosmos, are based on the assumption that we are in an average place. If we are inside an unusually dense region or perched on the edge of a gargantuan void, our measurements could be biased, giving us a distorted view of the entire universe. The hunt for these giants and the search for the true end of greatness is more than just cataloging record breakers. It is a direct test of the foundations of modern cosmology, a quest to see if the universe truly plays by the rules we have written for it, or if it has been hiding a grander, more complex architecture all along. But our exploration of the largest structures inevitably pulls our focus down to the very smallest, to the bizarre and counterintuitive world of quantum mechanics. It seems unbelievable that the rules governing particles smaller than an atom could have anything to say about the universe at its grandest scales, but this is where our journey takes a truly mind-bending turn. The same quantum principles that dictate how electrons behave around a nucleus might also hold the key to the very origin of the cosmos and the fabric of space-time itself. This brings us to a profound mystery. How do quantum fluctuations operate not in the lab, but across the entire expanse of the universe? And could they even look different out there on the cosmic frontier? To understand this, we have to start with a fundamental quantum concept. Emptiness is an illusion. What we perceive as a perfect vacuum is actually a seething, bubbling cauldron of activity. Due to the Heisenberg uncertainty principle, energy can spontaneously borrow into existence in the form of virtual particle pairs, a particle and its antiparticle, that flicker into life and then almost instantly annihilate each other, returning the energy back to the vacuum. This frantic activity is happening everywhere, all the time, at every point in space. It's called quantum foam, and it's the baseline state of reality. For decades, we thought these fluctuations were purely a microscopic phenomenon, their effects far too tiny to notice in our everyday, classical world. Yet, the most stunning revelation of modern cosmology is that the entire universe we see today might be the product of one particular set of quantum fluctuations, magnified to a cosmic scale. The theory of cosmic inflation proposes that a microscopic patch of space-time, fueled by a strange energy field, underwent a period of hyper-fast expansion, blowing up by a factor of trillions upon trillions in a fraction of a second. During this incredible growth spurt, the tiny quantum fluctuations in that primordial field were stretched from the subatomic to the astronomical. Those minuscule ripples in energy became the seeds for all future structure. The slightly denser regions, where a virtual particle pair happened to pop into existence and get frozen by inflation, became the gravitational anchors for galaxy clusters. The slightly less dense regions became the cosmic voids, Every galaxy, every star, every planet is here because of a random quantum event that happened when the universe was smaller than a proton. Our entire cosmic history is written in THE, Chinese letter, Chinese letter, Chinese letter of quantum noise. This incredible connection between the quantum and the cosmic forces us to ask a daring question. If quantum mechanics gave birth to the large-scale structure of the universe, does it still govern its behavior today? Specifically, does the strangest phenomenon in quantum physics, entanglement, work over cosmic distances? Entanglement is the deeply mysterious connection that can instantly link the properties of two particles, regardless of the distance between them. If you measure the spin of one entangled electron here on Earth, its partner, even if it's on the other side of the galaxy, will instantly assume a correlated state. This spooky action at a distance, as Einstein called it, seems to violate the cosmic speed limit of light, and it's been proven to work over hundreds of miles in lab experiments. But does it work over hundreds of millions of light years? Some physicists speculate that the answer might be no. They propose that there could be a fundamental decoherence mechanism, a kind of environmental noise on a cosmological scale that causes quantum systems to lose their coherence over such vast distances. The fabric of space-time itself, or the subtle influence of dark energy, might act to slowly untangle these quantum connections, forcing the universe to behave more classically on the largest scales. If this were true, it would mean there is a hidden boundary where quantum weirdness gives way to classical certainty, a frontier where the rules of physics themselves change. However, other theories go in the completely opposite direction, suggesting that entanglement might not just work over cosmic distances, but might actually be the glue that holds space-time together. The concept of ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind, suggests that what we perceive as a wormhole connecting two distant points in space, an Einstein-Rosen bridge, or might be the same thing as a pair of entangled particles, an Einstein-Podolsky-Rosen pair, or EPR. In this breathtakingly elegant idea, entanglement doesn't happen through space. It actually creates the geometric connection of space itself. This would mean that the entire universe is a vast, complex web of quantum entanglement, and the smooth geometry of space-time that we experience emerges from countless trillions of these invisible connections. The cosmic web of galaxies we see could be a shadow of a far deeper, quantum informational web. Testing these ideas is the monumental challenge facing a new generation of telescopes and experiments. Astronomers are now looking for the faintest possible signatures in the light from the most distant quasars and the cosmic microwave background, searching for any telltale sign that quantum rules have been subtly altered over billions of light years. They are, in effect, using the universe itself as the largest possible quantum physics laboratory. The answers they find won't just resolve a technical debate. They will tell us if the quantum and cosmic realms are truly separate domains governed by different rules, or if they are two sides of the same coin, woven together into a single, unified, and profoundly interconnected tapestry of reality. But if the universe is truly infinite and flat, as our best measurements suggest, that seemingly straightforward answer opens up a whole new realm of astonishing possibilities. We've been thinking of the cosmos as an endless, flat plane extending forever in every direction. But what if that flatness is just a local property? What if, on scales even larger than our observable horizon, this vast plane actually folds back on itself in a hidden, higher dimensional shape? This is the captivating mystery of the universe's topology, the study of its global shape and connectivity, a property that is completely separate from its local curvature. We're all familiar with basic topology in everyday life. The surface of a donut, a shape mathematicians call a torus, has a flat geometry. If you were a tiny ant living on that surface, you could walk in a straight line forever and never encounter an edge, and the angles of a triangle would always add up to 180 degrees, just like on a flat sheet of paper. But the global experience is completely different. On a truly infinite flat plane, you'd just keep going forever. On a torus, if you walked far enough in one direction, you'd eventually return to your starting point from the opposite side. The local geometry is identical, but the global topology is fundamentally different. The universe could be the same way. It could be measured as perfectly flat in every local region, yet still be a finite, closed shape without any boundaries. It could be a three-dimensional equivalent of a torus, or any number of other multiply-connected shapes. How could we possibly detect such a thing from our tiny vantage point? The most promising method involves looking for ghostly echoes in the oldest light we can see, the cosmic microwave background. If the universe does have a finite, wrapped shape, it's possible that the universe is not large enough to contain unique copies of every structure. The same cluster of galaxies, or even the same specific pattern of hot and cold spots from the Big Bang, could appear in multiple places on the sky. In fact, if the wrapping scale were smaller than the diameter of our observable universe, we might actually be able to see multiple copies of the same object, like seeing the same mountain peak from two different valleys. More precisely, cosmologists search for matched circles. The idea is that if space wraps around, a single massive object like a galaxy cluster could have its light travel along two different wraparound paths to reach us. In the CMB, this would appear as two perfect circles on opposite sides of the sky that have identical patterns of temperature fluctuations. It would be the ultimate cosmic fingerprint, undeniable proof that our universe is a finite, connected shape. Scientists have scoured the data from the Planck satellite and other probes, looking for these telltale matched circles. So far, they haven't found any convincing evidence. This doesn't rule out a complex topology entirely. It just means that if the universe is multiply-connected, the wrapping scale must be larger than our observable horizon. The fundamental cell of the universe's pattern would be bigger than the patch we can see, meaning we are, for now, trapped inside a single tile of a potentially repeating cosmic mosaic, unable to see the repeating pattern. This is a profoundly humbling thought. Even if the universe isn't infinite, its repeating pattern may be so grand that it remains effectively infinite from our perspective. Beyond the torus, the mathematical possibilities are dizzying. The universe's topology could resemble a three-dimensional Klein bottle, a shape with only one side, or a hyperbolic horn, or any number of other complex manifolds. Some theories even suggest the topology could be dynamic, changing over the history of the cosmos. The initial period of inflation might have stretched space so violently that it ironed out any small-scale wrappings, leaving behind a topology so vast we can never hope to observe it. Or perhaps those primordial wrappings are still there, hidden just beyond our view, waiting for a future generation of telescopes with a yet wider view to finally catch a glimpse of the universe's true, elegant, and finite shape. The search continues, not just for the geometry of space, but for its hidden connections, a quest to determine if our cosmic home is an endless expanse or a beautifully intricate, closed loop. Yet for all its remarkable success, this model of our universe's first moments harbors a single, glaring flaw, a small but persistent discrepancy that has stubbornly resisted explanation for decades. This is the cosmic lithium problem, and it serves as a quiet reminder that even our most successful theories might still be missing a crucial piece of the puzzle. The story begins with that same recipe, the one that so perfectly predicted the amounts of hydrogen and helium. The equations also make a very specific prediction for the next lightest element, lithium. According to the theory of Big Bang nucleosynthesis, the hot, dense infant universe should have produced a certain amount of lithium-7, an isotope that makes up about 92% of the lithium found naturally on Earth. The calculations are precise and elegant, grounded in well-understood nuclear physics. But when astronomers go out and actually measure the amount of lithium in the oldest stars in our galaxy, the numbers don't match. The oldest stars, known as population 2 stars, are thought to be pristine relics from the early universe. They formed from gas that had been polluted by nothing but the products of the Big Bang itself, making them perfect time capsules for measuring primordial element abundances. Yet when we analyze their atmospheres using spectroscopy, we find that they contain only about 1/3 to 1/2 the amount of lithium-7 that the Big Bang model predicts. It's not a small margin of error. It's a discrepancy of a factor of 2 or 3, and it has been confirmed repeatedly by different teams using different telescopes. This isn't just a minor accounting error. It's a fundamental mystery about the very ingredients that were available when the first stars began to shine. Scientists have been wrestling with this problem for over 30 years, and the solutions they've proposed fall into 3 broad categories. The first possibility is that our understanding of the nuclear physics itself is incomplete. The reactions that forge elements in the Big Bang's fiery crucible are incredibly complex, involving a chain of interactions between protons and neutrons. Perhaps there is a previously unknown nuclear reaction pathway that destroyed some of the lithium-7 as it was being formed. Or maybe the rates of some key reactions are slightly different than what we've measured in our laboratories here on Earth. While this seems like a straightforward fix, decades of meticulous work by nuclear physicists have only strengthened our confidence in the measured reaction rates, making this solution increasingly unlikely. This leads to the second and more popular category of solutions. Perhaps the lithium is destroyed after the Big Bang, inside those very same ancient stars we use to measure it. Stars are not static museums, they are dynamic furnaces. The outer layers of a star can circulate, dragging material from the surface down into the hot interior where it can be fused into different elements. This process, known as atomic diffusion or stellar convection, could slowly deplete the surface lithium abundance over billions of years, making it appear as if the star started with less lithium than it actually did. The challenge here is that our models of stellar physics must be incredibly precise to confirm this, and we would need to find a way to see past this depletion to the original amount. Some astronomers search for the lithium in the extremely tenuous gas between stars, hoping to find the missing atoms there, but so far, the results have been inconclusive. The third, and most exciting, possibility is that the lithium problem is a hint of new physics beyond our current standard models. The predictions of Big Bang nucleosynthesis depend critically on the conditions of the early universe, particularly the density of protons and neutrons and the expansion rate during those first few minutes. What if something altered those conditions? Some theorists have proposed the existence of exotic particles that were present in those first moments. For instance, a relatively light, electrically neutral particle known as an action could have been produced in the early universe. If it decayed during the period of nucleosynthesis, it would have injected extra energy, changing the reaction rates and potentially reducing the amount of lithium-7 that was formed. Other ideas involve modifications to gravity or even the tantalizing possibility that the fundamental constants of nature, like the strength of the forces between particles, were slightly different in the extreme environment of the newborn cosmos. The lithium problem is a perfect example of a small mystery with potentially enormous implications. It doesn't demand a complete overhaul of cosmology, but it points to a subtle crack in the foundation. Resolving it could either teach us something new about the intricate internal workings of the first stars, or it could fling open a door to a whole new realm of particle physics that operated only in the universe's first few minutes. It is a quiet, persistent whisper from the dawn of time, a two-fold deficit that challenges us to look deeper, both into the hearts of the oldest stars and into the fundamental laws that shaped our existence. But as we look ahead to the far future, a time of dark, evaporating black holes and the potential erasure of all structure, we are forced to confront one of the most perplexing puzzles in all of theoretical physics. a mystery that pits our two most successful theories against each other in an epic battle for the soul of reality. This is the black hole information paradox, and while it might seem like an abstract problem for physicists, its resolution could dictate the ultimate fate of every bit of information that has ever existed, from the first starlight to the memory of every living thing. To understand the paradox, we must start with two pillars of modern physics that are both incredibly successful and seemingly incompatible. The first is quantum mechanics, which governs the world of the very small. A cornerstone of this theory is the principle of unitarity, which essentially states that information is never truly lost. It can be scrambled, transformed, and become incredibly difficult to read, but it is never erased from the universe. If you could somehow reverse all the quantum mechanical processes, you could, in theory, reconstruct the entire history of every particle. The second pillar is general relativity, Einstein's theory of gravity, which describes the behavior of massive objects like black holes. According to general relativity, a black hole's event horizon is a point of no return. Anything that crosses it, whether a spaceship, a book, or a person, is lost forever to the outside universe. The black hole is described only by its mass, electric charge, and spin. It retains no other details about what fell in. This is poetically summarized as black holes have no hair. All the intricate information about the objects that formed it is seemingly obliterated. For decades, physicists could live with this tension, assuming the information was simply locked inside the black hole, permanently hidden but not destroyed. Then Stephen Hawking made a startling discovery. He realized that due to quantum effects at the very edge of the event horizon, black holes aren't entirely black. They slowly emit radiation, now known as Hawking radiation. This radiation causes the black hole to lose mass and, over astronomical timescales, completely evaporate. This is where the paradox sharpens to a point. Hawking's original calculations showed that this radiation is purely thermal. It's random noise like the heat coming off a stove. It contains no information whatsoever about what fell into the black hole. So if a black hole forms, swallows a bundle of information, and then evaporates away, leaving behind only this featureless thermal radiation, then the information it once contained has been irrevocably lost. This violates the sacred principle of unitarity in quantum mechanics, creating a fundamental contradiction at the heart of physics. This launched a crisis that has lasted for 50 years, with physicists proposing a myriad of potential solutions. One of the earliest ideas was that the information isn't really lost, it's just copied. Perhaps the information is both reflected at the event horizon, encoded in the Hawking radiation, and remains inside the black hole. But this violates another quantum rule, the no-cloning theorem, which forbids the perfect copying of quantum information. Another proposal is that black holes don't evaporate completely. They leave behind a tiny, stable remnant, a speck smaller than an atom that contains all the information that ever fell into the black hole, locked away forever. The problem with this idea is that it would require an almost infinite number of different types of these remnants to account for all the possible information they could store, which most physicists find to be an inelegant and unsatisfying solution. The most popular resolution to the paradox today, and one that ties directly into our cosmic fate, involves Hawking radiation itself. The modern consensus, though still not universally proven, is that the radiation is not completely random after all. The evaporation process is incredibly complex, and the interactions between particles escaping the black hole's gravitational grip may subtly encode the information about the black hole's interior. It's not that the information is carried out on individual particles of radiation. Rather, it's imprinted in the correlations between all the particles emitted over the black hole's entire multi-trillion-year lifetime. Decoding it would be like trying to reconstruct an entire library from the ashes of a book, burned one scrambled letter at a time over billions of years. It seems impossible from our perspective, but the laws of quantum mechanics insist the information is, in principle, preserved. This is where the scale of the cosmos becomes critical. In our current, vibrant universe, black holes are forming and new information is constantly being created. But in the far, far future, during the era of the heat death, the situation will be different. The universe will be dominated by the oldest, most massive black holes, which have consumed galaxies' worth of information, and they will be the last structures slowly evaporating away. If the information is preserved in their Hawking radiation, the final state of the cosmos would be a cold, dark, nearly empty vacuum, but a vacuum faintly buzzing with this low-energy radiation that contains, in an impossibly scrambled and dilute form, the entire history of the universe. Every star that ever shone, every planet that ever formed, and every thought that was ever thought would, in some sense, still be encoded in the fundamental quantum fields. The universe would become a silent, cosmic archive, preserving information for an eternity with no one left to read it. However, if the information is truly lost, the implications are even more profound. It would mean that the laws of physics as we know them are fundamentally incomplete. We would need a new, more advanced theory, likely a theory of quantum gravity that successfully merges quantum mechanics and general relativity. This is why the paradox is so important. It's not just a philosophical debate. It is a crucial stepping stone toward a deeper understanding of reality. Resolving it might require us to completely rethink the nature of space and time, perhaps seeing them as emergent properties from something more fundamental, like a vast network of quantum information. The final evaporation of the last black holes, trillions upon trillions of years from now, would then represent the ultimate erasure, a final deletion of cosmic history that would leave the universe not just empty, but truly meaningless. The black hole information paradox is therefore more than a puzzle. It is a question about whether the universe ultimately remembers itself, or if it is destined to forget everything it ever was. Now we arrive at a mystery so fundamental that it forced cosmologists to invent one of the most radical ideas in all of science just to solve it. It's called the horizon problem, and it asks a simple question with deeply complex implications. How did parts of the universe that have never been in contact with each other somehow agree on the rules? Imagine two people standing on opposite sides of a vast, darkened stadium, too far apart to see or hear each other. Suddenly, at the exact same moment, they both start clapping in perfect unison. You would immediately suspect they had some prior agreement or were receiving a signal from a common source. The cosmic microwave background presents us with exactly this kind of coordinated behavior on a scale that defies explanation. This fossilized light from the early universe shows a nearly perfectly uniform temperature across the entire sky, with only tiny 1 in 100,000 variations. Today, the two most distant points we can see in opposite directions are separated by over 93 billion light-years. Yet, the light from each of those points has only had 13.8 billion years to travel. There simply hasn't been enough time since the Big Bang for light, or heat, or any form of information to have traveled between them. They are, by definition, outside each other's causal horizons. They could never have exchanged a signal to coordinate their temperature. According to the standard Big Bang model, these regions should be completely disconnected and could easily have developed wildly different properties. The fact that they are almost identical is a profound puzzle. It's as if every room in a colossal mansion, with no connecting hallways, was preheated to exactly 70 degrees Fahrenheit without anyone ever communicating. The leading and most widely accepted solution to this problem is the theory of cosmic inflation. This idea proposes that a fraction of a second after the initial singularity, the universe was seized by a mysterious, repulsive energy field that caused it to expand at an exponential, faster-than-light rate. In this unimaginably brief period, a patch of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. Crucially, this entire vast region was once small enough to be in perfect thermal contact. Every part of it was cozy and close, allowing heat to spread evenly and establish a uniform temperature. Then, inflation blew it up, locking that uniformity into place across a colossal volume. The distant points that today seem forever out of touch were once intimate neighbors, which explains their identical temperature. Inflation doesn't just solve the horizon problem. It also elegantly explains why the universe is so flat and where the seeds for galaxies came from. They are simply quantum fluctuations from that primordial field, stretched to cosmic proportions. Yet, as compelling as inflation is, it remains a theory, and the search for direct evidence continues. This has led some scientists to propose alternative, even more radical explanations. One such idea is that the speed of light itself was not always constant. In the very early universe, light may have traveled much faster, allowing it to zip between these distant regions and smooth everything out before settling down to the constant speed we measure today. This variable speed of light theory is a dramatic departure from Einstein's relativity, but it offers a way to connect those distant horizons without invoking a period of hyper-expansion. Another possibility pushes the boundaries of causality even further. Perhaps the connection between these distant points wasn't made after the Big Bang, but before it. Some models of a cyclical universe, or theories involving a pre-Big Bang state, suggest that our entire observable cosmos was once part of a single, unified entity that had already achieved equilibrium. In this view, the uniformity was established in a previous cosmic cycle or in a larger meta-universe that our Big Bang emerged from. The horizon problem then becomes a non-issue because the connectedness is inherited from a broader reality that predates our own. Each of these solutions, from inflation to variable constants to a pre-existing state, forces us to reconsider the very nature of time, causality, and the beginning of everything. The horizon problem is more than a technical issue in cosmology. It is a direct challenge to our understanding of how cause and effect operate on the grandest of scales. It asks us to accept that either the universe underwent a period of expansion so violent it seems like magic, or that the fundamental constants of nature are not so constant after all, or that our universe's history extends far beyond the zero point of the Big Bang. The perfect uniformity of the cosmic microwave background, that serene and quiet afterglow, is actually the site of a tremendous cosmic paradox, one that continues to drive our search for a deeper theory of reality. Now, if the universe could so perfectly preserve information even in the face of a black hole's oblivion, it makes you wonder if there are other fundamental symmetries woven into the fabric of reality that we simply haven't found yet. This brings us to a classic and elegant puzzle, one that sits at the crossroads of particle physics and cosmology, the baffling case of the missing magnetic monopoles. We are all familiar with magnets. Every child who has ever played with a bar magnet knows it has two ends, a north pole and a south pole. You can break that magnet in half, but you won't get an isolated north or an isolated south. You'll just get two smaller magnets, each with its own north and south pole. This is a fundamental feature of electromagnetism as we know it, but many physicists find this deeply asymmetrical. In the world of electric charges, we have positive and negative particles that exist perfectly well on their own, like the proton and the electron. So why should magnetism be any different? Why are there no single, isolated magnetic poles? The equations of physics, particularly those of grand unified theories, actually suggest that such particles, called magnetic monopoles, should exist. These theories aim to merge the electromagnetic force with the weak and strong nuclear forces, describing a time in the very early universe when these forces were one and the same. A key prediction of these models is that as the universe cooled and this unified force broke apart, It should have created incredibly massive and stable particles carrying a single magnetic charge. So where are they? If these grand theories are correct, the early universe should have been flooded with monopoles. They would be so numerous and so stable that they should be everywhere today, overwhelmingly more common than even atoms. We should be tripping over them. The fact that we have never detected a single, unequivocal magnetic monopole is a massive problem, one that threatened to derail these beautiful theories before they even got started. This isn't just a minor oversight. It's a glaring absence that demands an explanation. One of the most compelling solutions, and a key reason the theory of cosmic inflation was developed, is that the monopoles are still out there, but they have been dramatically diluted to near invisibility. Imagine you have a single drop of ink and you place it in a swimming pool. The ink is still there, but finding that one specific drop in all that water is nearly impossible. Now, imagine that swimming pool is the size of the Pacific Ocean. This is what inflation may have done to magnetic monopoles. The theory proposes that a fraction of a second after the monopoles were created, the universe underwent that period of hyper-fast, exponential expansion. It stretched space itself by a factor of trillions upon trillions. Any monopoles that were created were suddenly flung impossibly far apart from one another, reducing their density in our observable universe to practically zero. In this view, the monopoles aren't missing. Our observable patch of the cosmos simply contains very few, or perhaps even just one of them. They are lonely relics from a more unified age, drifting in the immense voids between galaxy clusters. Another possibility is that we simply haven't looked in the right places or in the right way. Theoretical monopoles aren't just simple magnets. They are thought to be incredibly massive particles, perhaps as heavy as a bacterium, which is enormous by particle standards. They could be lurking in exotic locations, trapped within the intense magnetic fields of neutron stars, or even buried deep within the Earth. Some experiments have spent decades searching for them. They use sophisticated detectors like loops of superconducting wire that would produce a distinct electrical signature if a monopole passed through, effectively creating a current out of nothing. Others have scoured moon rocks and ancient geological formations, searching for evidence that a monopole once passed through and left a telltale trail of damage. So far, these searches have turned up empty, but the hunt continues, a testament to the perseverance of scientists chasing a ghost predicted by our most ambitious theories. There is, of course, a third and more unsettling possibility, that magnetic monopoles simply do not exist. Perhaps our grand unified theories, for all their mathematical elegance, are incorrect. Maybe the way the fundamental forces broke symmetry in the early universe did not produce these particles. This would force a major revision of our understanding of particle physics and the conditions of the very early cosmos. Alternatively, it could be that monopoles are not fundamental particles, but emerge as collective excitations in certain exotic materials known as spin ices. In these lab-created crystals, tiny, jostling magnetic moments can behave as if they are individual north and south poles, acting out a fascinating simulation of the real thing. But while these are fascinating for studying the physics of magnetism, they are not the cosmic, fundamental particles predicted by theory. The magnetic monopole mystery is a beautiful example of how a single, absent particle can hold such immense weight. Its existence would confirm a profound symmetry in the laws of physics and provide a direct window into the universe when it was a fraction of a second old. Its continued absence challenges the very frameworks we use to describe reality, pushing us to either find a clever way to explain why we can't see them or to boldly rethink our most cherished theories about the unity of nature. We have journeyed through the most profound enigmas at the edge of the universe, from the strange behaviors of dark matter to the ultimate fate encoded in dark energy. But these puzzles all stem from a single monumental event, the Big Bang. This forces us to confront what is perhaps the most fundamental mystery of all. What happened before the beginning, or more precisely, what were the universe's initial conditions, and why were they so perfectly, inexplicably tuned to allow for everything we see today? The standard Big Bang model describes the universe expanding from an initial state of immense density and temperature, but it is silent on what caused that state or what, if anything, preceded it. It simply starts there, a cosmic, initial condition that we must accept as a given. This is deeply unsatisfying to the scientific mind, which seeks causes and explanations. The problem becomes even sharper when we consider the concept of entropy, which is a measure of disorder. The natural tendency of any closed system is for entropy to increase, for things to move from order to disorder. Think of a hot cup of coffee cooling down in a room, or a neatly organized deck of cards becoming shuffled. The universe today is in a state of relatively high entropy. It's a messy, disordered place full of scattered energy. But to get to this messy state, it had to start in a state of unbelievably low entropy. The initial conditions of the Big Bang were like finding a mountain peak, meticulously carved into the shape of a perfect ice sculpture. The universe began in a state of exquisite, highly improbable order. All the matter and energy were crammed into an ultra-smooth, ultra-dense, and ultra-hot state, a configuration of incredibly low entropy. This low entropy beginning is the ultimate source of the arrow of time. It's the reason why we remember the past and not the future. Why ice melts in a warm room but never spontaneously forms from puddles. The profound mystery is, why did the universe start in such a special, ordered state? Who or what wound up the cosmic clock? Scientists have proposed several breathtaking possibilities to explain this. One idea is that our universe did not emerge from nothing, but from a prior state. Perhaps our Big Bang was not a true beginning, but a transition, a moment of rebirth from a previous cosmos. This is the core of cyclical universe models, like the conformal cyclic cosmology proposed by physicist Roger Penrose, or the ekpyrotic model born from string theory. In these visions, the universe undergoes an endless cycle of expansion, contraction, and rebirth. The catastrophic Big Crunch of one epoch becomes the Big Bang of the next. In this view, the low entropy of our beginning is not a one-time miracle. It is reset at the start of each new cycle, perhaps through some physical process we don't yet understand. The appeal is clear. It avoids a definitive beginning and offers a potentially infinite timeline. A second, and even more radical, idea is that the universe truly did emerge from nothing. But this nothing is not an empty void. It is a complete absence of space, time, and matter. Through the bizarre laws of quantum mechanics, where temporary fluctuations of energy are allowed, the universe could have spontaneously tunneled into existence from a state of nothingness. In this scenario, the initial low entropy is simply a property of this quantum genesis. The universe appeared in the lowest entropy state possible because that is the most probable state for a universe to pop into being. This idea, while philosophically staggering, pushes the limits of what physics can currently describe or test. A third perspective suggests that our question is based on a flawed assumption. Perhaps the initial conditions weren't special at all, but only appear that way from our limited viewpoint. This is the core of the multiverse hypothesis. If an infinite number of universes are constantly bubbling into existence, each with random initial conditions, then it's no surprise that we find ourselves in one of the rare universes where the entropy was low enough to allow for galaxies, stars, planets, and life to form. In most universes, the entropy was high from the start, leading to immediate heat death and no observers. We are here because we won the cosmic lottery, and our presence selects for a universe with these seemingly fine-tuned beginnings. The mystery of the initial conditions is then not a puzzle to be solved, but a consequence of our own existence, an idea known as the anthropic principle. Each of these possibilities a cyclical universe, a quantum genesis from nothing, or a multiverse selection effect strains our intuition to the breaking point. They challenge our very notions of cause and effect, of time and existence. The search for an answer is not just about finding a mathematical model that works. It is about uncovering the deepest laws of reality that govern whether something can come from nothing, and why our universe is so hospitable to complexity and life. The initial conditions are the ultimate foundation upon which every other cosmic mystery is built. A silent, perfect, and profoundly mysterious starting gun for the history of everything. This profound connection between the quantum and the cosmic, this seeding of galaxies by subatomic uncertainty, forces us to confront a bizarre and fundamental question that physicists have debated for a century. If a quantum particle exists in a blurry cloud of potentialities, a superposition of many possible states, what causes it to finally pick one definite reality when we observe it? This is the core of the measurement problem, a puzzle that lies at the heart of quantum mechanics. For a single electron in a lab, this is strange enough. But we must now ask, does this act of observation, this so-called collapse of the wave function, work the same way when we're talking about an entire galaxy, or a supercluster, or the universe itself? Is there a point where the sheer scale of a system changes the quantum rules? The standard interpretation, often called the Copenhagen interpretation, suggests that a conscious observer is ultimately responsible for collapsing the wave function, for turning possibility into actuality. This is a troubling idea when applied to the cosmos. It seems to suggest that before the first conscious beings evolved to look up at the stars, the entire universe existed in a fuzzy, undefined superposition. Were galaxies, in a sense, not really there until someone observed them? This seems not only illogical but also incredibly anthropocentric, placing human consciousness at the center of cosmic reality. Most physicists find this interpretation unsatisfying for the large scale, leading them to explore other, even stranger possibilities. One compelling alternative is the idea of spontaneous collapse. This theory proposes that wave functions don't need a conscious observer to collapse. They do it on their own, and the rate of collapse depends on the size or complexity of the system. For a single electron, it might stay in a superposition for a long time. But for a macroscopic object made of trillions of atoms, like a planet, a star, or a telescope, the collapse happens almost instantaneously. In this view, the quantum weirdness is constantly being suppressed by the sheer mass and scale of large objects. The universe's largest structures didn't need us to look at them to become real. Their own immense size forced their wave functions to collapse eons ago. This provides a natural, physical mechanism for how the classical certainty of the cosmic world emerges from the quantum fog of the microscopic. Then there is the mind-bending many worlds interpretation, which boldly declares that the wave function never collapses at all. Instead, every possible outcome of every quantum event actually happens, but each outcome unfolds in its own separate, non-communicating branch of reality. In this view, the universe is constantly splitting into a multiverse of near-infinite possibilities. At the moment of the Big Bang, a near-infinite number of universes were born, each with a slightly different set of those initial quantum fluctuations. In one branch, a particular galactic supercluster formed exactly as we see it. In another branch, it formed slightly differently. In another, it didn't form at all. There is no single, definitive history of the cosmos, but rather a tapestry of all possible histories, all equally real. This interpretation completely sidesteps the measurement problem by saying that what we perceive as collapse is merely our conscious experience following one specific branch of an endlessly forking tree. So how could we possibly test these abstract philosophical ideas against the cold, hard reality of the cosmos? Astronomers are turning the universe itself into a massive laboratory. One method involves looking for the faintest possible light from the most distant quasars. the brilliant cores of active galaxies. As this light travels for billions of years through the expanding universe and the tenuous fog of the intergalactic medium, any tiny, residual quantum fuzziness in the fabric of space-time itself could subtly alter its properties. If spontaneous collapse models are correct, the effect should be imprinted on this ancient light in a specific, detectable way. Another approach is to scrutinize the cosmic microwave background with incredible precision. The pattern of fluctuations we see is a frozen quantum snapshot. If the many worlds interpretation is correct, and every possible outcome is realized somewhere, our universe's specific pattern might appear slightly more typical or likely than what we'd expect if ours were the only reality. We are, in effect, searching for shadows of other universes in the imperfections of our own. The measurement problem at cosmic scales is ultimately a question about the nature of reality itself. Is the universe we see a single, objective, classical structure that exists independently of us, as spontaneous collapse suggests? Or is it just one thread in an infinitely rich multiversal tapestry, as the many worlds interpretation claims? Or does consciousness truly play some mysterious role in bringing the cosmos into focus? These are not just questions for physicists in a lab. They are foundational to our understanding of existence. The answers, if we can ever find them, will tell us whether the majestic galaxies we see are solid, singular truths, or merely the branch of reality we happen to be walking on. These immense, seemingly empty regions between the threads of the cosmic web are not just passive blanks. They are active players in the evolution of the universe, and their origins and contents are a profound mystery. A cosmic void is far more than just a place where a few galaxies are missing. These are staggering deserts of space, some stretching over 350 million light-years across. To put that in perspective, if our Milky Way were the size of a grain of sand, crossing one of these voids would be like traveling the distance between New York and London. Within these caverns, the density of galaxies can be 10 to 100 times lower than the cosmic average. They are the universe's emptiest places, but emptiness in space is a relative term, and it's what might be hiding within that emptiness that fuels scientific debate. One of the leading theories for their formation is surprisingly straightforward, rooted in the very same gravitational processes that built the galaxies themselves. Imagine the early universe after the Big Bang, a nearly smooth soup of matter with tiny, quantum fluctuation ripples. Over billions of years, gravity acts as an amplifier. The slightly denser regions pull in more and more matter, growing into galaxies and the dense filaments of the cosmic web. Conversely, the slightly less dense regions get left behind. As matter flows out of these underdense areas and into the surrounding filaments, the voids expand and deepen. It's a gravitational landslide on a cosmic scale. In this view, voids are simply the inevitable and natural inverse of the clusters. They are the valleys carved out by the same forces that built the mountains. Their sheer size and emptiness are a direct result of this relentless drainage over eons. However, their profound emptiness has led to more exotic proposals. Could these voids be more than just evacuated regions? Could they be the primary reservoirs for the universe's most mysterious component, dark energy? We know dark energy is causing the expansion of the universe to accelerate, but we don't know if its strength is perfectly uniform everywhere. Some theories suggest that dark energy might be concentrated in these empty spaces. Think of it like this. If dark energy is a property of space itself, then where there is the most space, the most pure vacuum, its repulsive effect might be strongest. In this scenario, a void wouldn't just be expanding with the rest of the universe. It would be pushing itself apart from the inside, actively accelerating its own growth and contributing disproportionately to the overall expansion of the cosmos. The void becomes an engine of isolation, relentlessly pushing galaxies away from its center and ensuring its own emptiness. This idea connects to one of the most radical possibilities. that the physical constants themselves, like the strength of gravity or the speed of light, could be different inside a void. Our entire understanding of physics is built on observations within our own galactic neighborhood, a region of relatively average density. But what if the rules of the game change in these extreme low-density environments? This concept is related to theories of modified gravity, which propose that our understanding of gravity is incomplete and that it behaves differently where its pull is exceedingly weak. In the deep quiet of a void where the gravitational field is almost negligible, perhaps a different set of physical laws takes over. It's a haunting thought that the fundamental rules of reality might not be universal, but could instead depend on your address within the cosmos, with the voids representing realms where the familiar laws of physics have simply gone quiet. Observing these voids directly is a monumental challenge precisely because they are so empty. Astronomers use them as natural laboratories in a unique way, by studying what isn't there. They meticulously map the distribution of galaxies to define the void's boundaries. Then, they use a phenomenon called gravitational lensing. Even though a void has very little mass, its immense volume means it still has a gravitational signature. It's a hill of negative gravity. When light from a distant galaxy passes through a void, its path is subtly altered, not by being pulled inward, but by being pushed outward slightly compared to the surrounding denser regions. By measuring this incredibly faint distortion, scientists can weigh the void, or more accurately, weigh the lack of matter within it. This helps distinguish between a void that is truly empty and one that might be filled with a smooth, undetected distribution of dark matter or dark energy. The largest of these voids, like the Boötes void, present their own special puzzles. Discovered in the 1980s, it was initially found to be so devoid of galaxies that it was nicknamed the Great Nothing. While later surveys found a few dozen galaxies scattered within its vast volume, its emptiness remains shocking. The existence of such a colossal void so early in the universe's history is difficult to explain through gravitational formation alone. It may point to an extraordinarily large initial underdensity in the primordial universe, a single massive quantum fluctuation that was stretched to an immense scale by inflation. These supervoids might be the fossil imprints of the rarest kinds of fluctuations from the birth of the cosmos, making them not just empty spaces, but unique windows into the very first moments of time. They stand as silent, expansive monuments to the randomness of creation, challenging us to understand whether their void is a simple absence or a space humming with different, hidden rules. But this seemingly straightforward narrative of a singular beginning immediately presents us with a puzzle that stretches the very limits of physics and philosophy. If the universe and time itself began at the Big Bang, then the concept of before becomes meaningless. Asking what happened before the Big Bang is like asking what is north of the North Pole. Time, as we understand it, is a property of our universe, a dimension that came into existence along with space and matter. In this view, there simply was no before, because there was no time for anything to happen in. The question itself might be a category error, a misapplication of a concept that only makes sense within our cosmic bubble to a context where it no longer applies. Yet, the human mind is wired to seek causes and origins. We instinctively want to know what sparked the initial conditions, what set the cosmic clock ticking. This has led physicists to develop breathtaking theories that, in effect, find a way to have a before by redefining the nature of existence itself. One of the most prominent ideas is eternal inflation, which extends the inflationary theory we discussed earlier. In this scenario, our Big Bang was not a unique event, but merely one bubble among countless others in a much larger, eternally inflating multiverse. The inflationary energy field that drove our universe's rapid expansion never completely turns off everywhere. Instead, it continues to stretch the fabric of a meta-universe, a background reality in which new bubble universes are constantly spawning. In this view, our entire cosmos is just one island in an infinite archipelago, and the time before time is simply the infinite history of this eternal inflationary background, a realm where the laws of physics might be completely different from our own. Another profound possibility is offered by cyclic models, which propose an endless sequence of universes. The most well-known is the ekpyrotic model, inspired by string theory, which suggests our universe exists on a three-dimensional membrane, or brane, floating in a higher dimensional space. Collisions between our brane and a neighboring one could provide the immense energy required to create a new hot, dense state that looks exactly like a Big Bang, resetting the cosmic cycle. Roger Penrose's conformal cyclic cosmology offers a different kind of cycle, suggesting that the far, far future of our universe, a cold, empty expanse of scattered particles and evaporated black holes, becomes mathematically indistinguishable from the ultra-smooth, low-entropy state of a new Big Bang. In this elegant vision, the end of one eon seamlessly becomes the beginning of the next, in an infinite loop where time has no true start or finish, only transformations. Each of these theories pushes past the singularity, offering a potential window into a reality that predates our own, but they all require us to abandon our everyday notions of cause and effect. In a multiverse or a cyclic cosmos, the initial conditions of our universe are no longer a mysterious starting point. They are simply an outcome, an inheritance from a previous state of affairs. The exquisite fine-tuning that allowed for galaxies and life might be explained by random chance across infinite possibilities, or by physical laws that transcend a single universe. The question of what happened before shifts from a search for a first cause to an exploration of a deeper, perhaps eternal, reality whose laws we are only beginning to glimpse. Whether these ideas can ever be tested remains an open challenge, but they represent a monumental effort to answer one of the most fundamental questions we can possibly ask, pushing our understanding to the very edge of meaning itself. Yet for all the apparent randomness of galactic spins and cosmic structures, a deeply controversial idea has emerged from the data, one that would shatter a foundational pillar of cosmology if proven true. This is the startling claim that the universe itself might have a preferred direction of spin, a subtle but coherent rotation imprinted on the largest scales of reality. The cosmological principle, which states that the universe is homogeneous and isotropic, meaning it looks the same in every direction and has no special place, would be instantly overturned by such a discovery. It would mean the cosmos has a kind of cosmic north, a fundamental axis that breaks the symmetry we have always assumed was perfect. The evidence for this extraordinary claim comes from painstaking statistical analyses of galaxy rotation. Large-scale surveys like the Sloan Digital Sky Survey have mapped the spins of millions of spiral galaxies. While most galaxies show no obvious correlation, some studies have reported a faint but persistent signal, an alignment in the direction of rotation for galaxies separated by staggering distances. Their spins appear to be coordinated, not by local interactions, but as if they were all embedded in a vast, slowly rotating cosmic whirlpool. The scale of such a structure would be almost unimaginable, spanning billions of light years and implying a coherence that defies our standard model of the universe's formation. Gravity, which builds structure from tiny, random fluctuations, should not be able to create organization on such a monumental scale. Naturally, such a radical claim is met with intense skepticism and rigorous scrutiny. Critics argue that these alignments could be the result of subtle observational biases or systematic errors in how we measure galaxy rotation. For instance, the method for determining a distant galaxy's spin axis can be incredibly complex, relying on the careful analysis of its Doppler shift, which side is moving toward us and which is moving away. Imperfections in the data or in the algorithms used to process it could inadvertently create a false signal of correlation where none exists. The scientific process is now in full swing, with independent teams reanalyzing the same data with different techniques and waiting for new, even larger surveys to either confirm or finally refute the pattern. Should the evidence for a universal rotation hold up, the implications would be nothing short of revolutionary, pointing to physics beyond our current understanding. One possibility is that this rotation is a fossil relic from the very birth of the universe. Perhaps the primordial singularity possessed some form of initial angular momentum, a spin that was locked into the fabric of spacetime itself during the Big Bang, and has been imprinted on all structure that formed thereafter. This would mean our universe is not just expanding, but also gently rotating on a scale we are only now beginning to perceive. Another, even more exotic idea ventures into the realm of quantum gravity, suggesting that the fundamental structure of spacetime might have a built-in handedness or chirality at its most basic level, a property that manifests as this large-scale preference for rotation. This search for a cosmic axis is not happening in isolation. It intriguingly echoes another great mystery we discussed earlier, the so-called axis of evil, found in the cosmic microwave background. The potential alignment of these two independent anomalies, one in the ancient light of the Big Bang and another in the modern architecture of galaxies, would be incredibly difficult to dismiss as coincidence. It would strongly suggest that we are not just dealing with a statistical fluke, but with a real, physical phenomenon that has influenced the universe from its first moments to the present day. The hunt for a universal rotation is therefore more than an academic curiosity. It is a direct assault on one of our most cherished assumptions about the cosmos, a high-stakes investigation into whether the universe truly has no favorite direction, or if we have just begun to read its hidden, spinning blueprint. For centuries, the fundamental constants of nature have been the bedrock of physics, the unchanging numbers that dictate the rules of reality. The speed of light, the strength of gravity, the mass of an electron. These are the fixed parameters written into the cosmic code, the universal settings that allow atoms to form and stars to shine. We built our entire understanding of the cosmos on the assumption that these constants are, well, constant. The laws of physics you learn in a lab in London are exactly the same as those governing a galaxy a billion light-years away. But what if that's not true? What if the very rules of the game change over cosmic distances or deep time? This is the profound and controversial mystery of varying constants. The prime suspect in this investigation is the fine structure constant, often denoted by the Greek letter alpha. This isn't a single force, but a breathtakingly precise combination of three other constants: the charge of the electron, the speed of light, and Planck's constant. Its value, approximately 1/137th, governs the strength of the electromagnetic force, which is responsible for holding atoms together, for chemical reactions, and for the very nature of light itself. It is a magic number that seems perfectly tuned for complexity. If it were even slightly different, stars wouldn't fuse carbon, and life as we know it would be impossible. The search for changes in this constant turns the universe into a natural time machine. When we look at the most distant quasars, we are seeing light that has been traveling for billions of years. As this ancient light passes through interstellar gas clouds on its way to us, specific elements in those clouds like iron, magnesium, and nickel absorb very particular wavelengths of light. These absorption lines act like a unique barcode for each element. By analyzing the precise spacing and position of these barcodes in the light from quasars, astronomers can effectively conduct a forensic analysis of the laws of physics as they were billions of years ago. For over 2 decades, a team of scientists has been doing exactly this, and their results have sent shockwaves through the physics community. Their data, gathered from the world's most powerful telescopes like the Very Large Telescope in Chile, suggests a tantalizing pattern. The absorption lines from these ancient gas clouds do not perfectly align with the lines we measure in laboratories on Earth today. The discrepancy is incredibly small, a shift of just a few parts in a million, but it is persistent. Their analysis of hundreds of quasars points to the fine structure constant being slightly weaker in the distant past. And intriguingly, the change seems to depend on direction, as if there is a preferred axis in the universe where the laws of physics are slightly different. They've even given this potential axis a name, the Australian dipole, as the effect appears to be stronger when looking toward one particular hemisphere of the sky. Naturally, a claim this extraordinary faces intense scrutiny and demands extraordinary evidence. The primary challenge is systematic error. Measuring these incredibly faint, ancient spectral lines is a Herculean task. The light is dim, the instruments are complex, and any tiny miscalibration or unaccounted for effect within the telescope or spectrograph could mimic the signal of a changing constant. Other research teams, using different methods and telescopes, have failed to confirm the result, finding no evidence that alpha has changed. The scientific community remains sharply divided, with some hailing it as a revolutionary discovery and others dismissing it as an elaborate, persistent artifact of measurement. But let's assume for a moment that the findings are correct. What would it mean if the fine structure constant, or any fundamental constant, were not constant? The implications would be nothing short of earth-shattering. It would mean that the laws of physics are not universal and timeless. They are local and evolving. The universe would not have a single, unchanging set of rules, but rather a tapestry of physical laws that could vary from place to place and from era to era. This would immediately point to a reality far stranger than we've imagined, suggesting that the constants are not fundamental bedrock, but perhaps emergent properties, like temperature or pressure, that arise from deeper, unknown processes. Such a discovery would be a major clue in the quest for a unified theory of everything. Our current best theories, like the Standard Model of particle physics, treat these constants as fixed inputs. If they are found to vary, it would force a radical revision of these models, potentially providing a direct pathway to a deeper theory that can explain why the constants have the values they do. It could mean that what we perceive as our four-dimensional reality is a shadow of a higher dimensional existence, where these constants are not fixed but fluctuate. The idea of a perfectly uniform cosmos, a cornerstone of modern cosmology, would have to be abandoned, replaced by a more complex and dynamic vision of reality, where the very fabric of physics is woven with threads that change color across the vast expanse of space and time. But as we peel back the layers of the cosmic microwave background and the faint whispers from the dawn of time, we uncover an even more elusive fossil, a ghostly echo that predates the first light itself. This is the cosmic neutrino background, a sea of nearly massless particles that has been flowing through the universe and through you since the first second of the Big Bang. While the cosmic microwave background shows us the universe at 380,000 years old, the neutrino background is a snapshot from when the cosmos was just 1 second old. It is the oldest known relic in existence, a breathtakingly ancient messenger carrying secrets from a time before atoms, before light could even travel freely. Neutrinos are the ghosts of the particle world. They are produced in abundance in nuclear reactions, from the sun's core to the titanic explosions of supernova, but they famously refuse to interact with normal matter. Trillions of them are passing through your body every second, leaving absolutely no trace. The cosmic neutrino background is the primordial source of all these particles. In the unimaginable heat of the universe's first second, particles and energy were in a constant, violent dance. But as the cosmos expanded and cooled, roughly 1 second after the Big Bang, it reached a temperature where neutrinos, which had been constantly slamming into other particles, suddenly found they could travel without obstruction. They decoupled from the rest of the cosmic soup and have been streaming freely through the universe ever since, a permanent, silent witness to the moment reality cooled enough to set them free. Detecting this background is arguably the most difficult challenge in all of observational astronomy. The problem is their incredible feebleness. These primordial neutrinos have been traveling for 13.8 billion years, and the expansion of the universe has stretched their wavelengths and sapped their energy to a breathtakingly low level. Today, it's estimated that every cubic centimeter of space, a volume about the size of a sugar cube, contains around 336 of these relic neutrinos. But they each carry so little energy that they are effectively frozen, moving at a fraction of the speed of light. Catching one is like trying to hear a single, specific whisper in a hurricane. Our current detectors, like the enormous Super Kamiok, and in Japan, are brilliant at detecting higher energy neutrinos from the Sun or distant galaxies, but they are completely blind to these ultra-low energy Big Bang relics. Their signals are simply too weak to trigger a reaction. So how could we ever hope to observe them? Scientists are pursuing two ingenious, long-shot strategies. The first is a direct detection method that borders on science fiction. It involves building a detector of staggering sensitivity, one that could register the minuscule amount of energy transferred if a primordial neutrino were to actually bump into an atomic nucleus. This would require a detector with a target mass of at least 100 tons, cooled to a fraction of a degree above absolute zero, and placed in the deepest underground laboratory to shield it from any other vibration or particle. It's a monumental engineering challenge that may not be possible for decades. The second strategy is an indirect one, looking for the ghost's shadow in the cosmic microwave background. When the neutrinos decoupled, they carried away a significant amount of energy, which subtly influenced the rate of the universe's expansion, and the way matter began to clump together. The precise pattern of fluctuations we see in the CMB today has been shaped by this sea of neutrinos. By measuring the CMB with exquisite precision, we can essentially weigh the neutrino background and confirm its properties, even if we can't hear its individual whispers. The scientific payoff for successfully detecting this background would be nothing less than revolutionary. First, it would provide direct, incontrovertible evidence for the hot Big Bang model itself, giving us a pristine probe of the universe at an epoch we can never see with light. Second, it could reveal the absolute mass of the neutrino. We know from other experiments that neutrinos have a tiny mass, but we don't know exactly what it is, or even what the mass hierarchy is between the three different types. The cosmic neutrino background would hold the answer, as its properties are exquisitely sensitive to the mass of its particles. But perhaps most tantalizingly, this ancient sea of particles could be the key to unlocking the mystery of dark matter. Some theories propose that dark matter particles could interact with these relic neutrinos in a subtle way, perhaps slowing them down or leaving a faint imprint on their distribution. Finding an anomaly in the cosmic neutrino background could be our first indirect glimpse into the dark sector, a realm of physics that has otherwise remained completely hidden. This invisible ocean from the first second of time is not just a cosmic artifact. It is a hidden library, and we are only now learning how to read its pages. Considering the staggering scale of the cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars and likely even more planets, the sheer number of opportunities for life seems almost infinite. The universe appears to be a place teeming with potential, a vast ocean of suns where islands of life should be commonplace. And yet, when we train our most powerful instruments on the sky and listen for any sign, any whisper of intelligence beyond our own, we are met with a profound and unsettling quiet. This is the Fermi paradox, the stark contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them. It's a mystery that forces us to confront not just the nature of life in the universe, but our own future within it. The core of the paradox is beautifully simple. Enrico Fermi, the famed physicist, reportedly posed the question over lunch one day in the 1950s. Where is everybody? His reasoning was straightforward. Given the age of the universe, which is over 13 billion years old, and the fact that our own galaxy is over 10 billion years old, there has been more than enough time for an intelligent species to arise, develop advanced technology, and spread across the Milky Way. Even traveling at a tiny fraction of the speed of light, a civilization could theoretically colonize the entire galaxy in a few tens of millions of years, a mere blink of the eye on cosmic timescales. The galaxy should be buzzing with activity, filled with the artifacts and transmissions of countless civilizations, but from our vantage point, it appears empty and silent. This silence is what astronomers call the Great Silence, and it is one of the most perplexing puzzles we have ever encountered. Scientists and thinkers have proposed a vast spectrum of solutions to this paradox, which generally fall into two broad and sobering categories. The first set of answers suggests that intelligent, technological life is extraordinarily rare. Perhaps the chain of events needed to go from non-living chemistry to a spacefaring civilization is so long and fraught with peril that it almost never happens. This is the concept of the Great Filter. The idea is that there is some stage in the evolutionary process that is incredibly difficult to get past. This filter could lie in our past. Maybe the emergence of life itself from inorganic matter is a miraculous fluke. Or perhaps the jump from simple prokaryotic cells to complex eukaryotic cells is an event of such staggering improbability that it has only happened once in our galaxy. If this is true, we might truly be alone, the only sentient beings for countless light years, living on a precious and lonely island in a silent sea of stars. The second, and perhaps more frightening, possibility is that the Great Filter lies in our future. This hypothesis suggests that the development of advanced technology inevitably leads to a civilization's destruction. It could be that once a species gains the power to alter its world on a global scale, it also gains the power to destroy itself. This could happen through nuclear war, a runaway engineered pandemic, or an uncontrollable nanotechnology event. Or the threat could come from artificial intelligence, a creation that surpasses its creators and decides it no longer needs them. In this grim view, the Great Silence is a galactic graveyard. The skies are empty not because no one was ever there, but because every civilization that has ever reached our level of technological adolescence has already succumbed to its own inventions. We don't hear anyone because they are all already gone, and we may simply be next in line. There are, of course, less apocalyptic explanations. It's possible that spacefaring civilizations are out there, but they are so advanced that we are simply incapable of perceiving them. Their technology and modes of communication might be as incomprehensible to us as a smartphone would be to a bacterium. They might have moved beyond using radio waves, which we primarily listen for, and instead use neutrino signaling or some other physics we have yet to discover. Or they might be deliberately hiding, a concept known as the zoo hypothesis. In this scenario, Earth is like a protected wildlife preserve, and more advanced civilizations are observing us from a distance, following a strict policy of non-interference until we reach a certain level of maturity. The silence, then, is not a sign of absence, but of a universe that is watching us, waiting to see if we pass our own greatest test. Yet after confronting the profound silence that may define our cosmic neighborhood, we are drawn back to a more fundamental question about the architecture of reality itself, one that challenges our very understanding of existence. Is the cosmos we call home finite, bounded by some unimaginable edge, or is it truly infinite, stretching without limit in every direction? This is not merely a philosophical musing. It is a question that modern cosmology is desperately trying to answer, and the implications are so staggering they defy belief. The most powerful evidence we have comes from those precise measurements of the cosmic microwave background, the afterglow of the Big Bang. As we discussed, the apparent size of the temperature fluctuations in this ancient light acts as a cosmic ruler, revealing the geometry of the universe. The data from the Planck satellite and other missions is incredibly clear. To within a tiny margin of error, the universe is geometrically flat. This measurement is profound because in the language of cosmology, geometry is destiny. A flat universe has zero curvature, meaning that the rules of Euclidean geometry we learned in school, that parallel lines never meet, and the angles of a triangle always add up to 180 degrees hold true on the largest imaginable scales. And this flatness points overwhelmingly toward an infinite universe. Just as a flat, two-dimensional sheet of paper can, in theory, extend forever in both directions, a flat, three-dimensional universe could extend without any boundary or end. The total volume of space, the number of galaxies, and the amount of matter would be literally without limit. But we must pause at that word, infinite. It is a concept that the human brain is simply not wired to grasp. We live in a world of finite objects, a finite number of people, a finite number of grains of sand on a beach, a finite number of stars in our galaxy. The idea of an endless cosmos is existentially dizzying. If the universe is infinite, then it isn't just very big, it is truly without end. Every single possible configuration of matter, no matter how improbable, must exist somewhere. This leads to one of the most mind-bending consequences imaginable, the concept of identical copies. In an infinite universe, there is not just one Earth, there are an infinite number of Earths. There is not just one of you, there are an infinite number of versions of you, living out every possible permutation of your life. Some versions are reading this very sentence in a nearly identical reality. Others made a slightly different choice years ago and are living a completely different life. And still others exist on planets where life never evolved at all. The infinite universe becomes a cosmic library containing not just every book that ever was or could be written, but every possible variation of every letter within those books. This idea, while thrilling, is also deeply unsettling. It challenges our sense of uniqueness and individuality. It suggests that every tragedy and every triumph has happened, is happening, and will happen again an infinite number of times across the endless cosmic expanse. However, it's crucial to understand the caveat. For these perfect copies to exist, the universe must not only be infinite in size, but also have a finite number of ways to arrange fundamental particles, a concept physicists call a finite Hilbert space. If the basic building blocks of reality can only be arranged in a finite number of stable configurations, then in an infinite volume, repetition becomes not just probable, but inevitable. The distances involved are, of course, unimaginably vast. These duplicate Earths would be located far beyond our cosmological horizon, forever out of reach due to the accelerating expansion of the universe. We could never visit them or receive a signal from them, but the sheer mathematical logic of infinity suggests they must be there. Yet, the story is not quite so simple. That tiny margin of error in our measurements of flatness leaves the door slightly ajar for other possibilities. The universe could have a very slight positive curvature, meaning it would be closed, like the surface of a four-dimensional sphere. In this scenario, the universe would be finite but unbounded. If you could travel in a perfectly straight line for long enough, you would eventually return to your starting point from the opposite direction, without ever hitting a wall or an edge. The total volume of such a universe could be enormous, perhaps many times larger than our observable horizon, but it would not be infinite. There would be a finite number of galaxies, a finite number of particles, and a finite number of possible histories. You would be unique. Your planet would be unique. The comforting, terrifying promise of infinite copies would vanish. Alternatively, the universe could have a slight negative curvature, shaping it like an infinite saddle. This would also be an infinite universe, but one with a more complex, open geometry. The current data fiercely constrains these options, pushing us toward the flat and infinite model, but that whisper of uncertainty is what keeps cosmologists looking for ever more precise data. The quest to measure the universe's curvature is, in essence, a quest to determine whether we live in a cosmos of boundless possibility or a vast but closed island of uniqueness. The answer defines not only the scale of reality but the very nature of our place within it. But if the very fabric of reality can be thought of in terms of information, this leads us to a profound and almost surreal question about the entire cosmos. How much information does the universe actually contain? And could this quantity be a fundamental property that shapes cosmic evolution itself? This isn't about counting bits on a hard drive. It's about understanding whether the cosmos, at its most fundamental level, might be built not just of matter and energy, but of information. To grasp this, we need to start with a surprising connection: the link between information and entropy. In our everyday language, entropy means disorder or chaos. But in physics, it's a precise measure of unpredictability. And in information theory, pioneered by Claude Shannon, entropy measures the amount of hidden information in a system, the number of yes or no questions you'd need to ask to precisely describe its state. A system in perfect order, like a crystal, has low entropy and contains very little information because it's highly predictable. A system in total disorder, like the smoke from an extinguished candle, has high entropy and contains a vast amount of information because you'd need an enormous number of bits to describe the exact position of every single smoke particle. The universe started in a state of incredibly low entropy, that smooth, ultra-dense soup of the Big Bang, and has been evolving toward higher entropy ever since, becoming more complex and more information-rich as it expands and structures form. So, how do we even begin to calculate the total information content of everything? One approach is to ask, what is the smallest possible piece of information that can be stored in a region of space? This leads to the concept of the Planck length, a distance so tiny that it's a trillionth of the width of a hydrogen atom. This is the scale where the smooth fabric of space-time is thought to break down into a frothing quantum foam. Some theories suggest that space itself might be pixelated at this scale, that there's a fundamental limit to how small a piece of information can be. If that's true, then you could calculate the total information capacity of the observable universe by dividing its volume by the volume of a tiny Planck-sized cube, and assigning one bit of information to each cube. This calculation yields a number so vast it defies human comprehension. Around 10 to the power of 120 bits. That's a 1 followed by 120 zeros. This number represents the maximum number of yes or no questions you could possibly ask to describe every detail of our entire cosmic horizon. But here's where the mystery deepens into the truly extraordinary. The holographic principle, an idea born from the study of black holes, suggests that this unimaginably huge number might be a massive overcount. When something falls into a black hole, it seems to vanish, but its information isn't lost. Stephen Hawking's work and its subsequent resolution suggest that this information is somehow encoded on the black hole's event horizon, its two-dimensional surface. The amount of information a region of space can contain is not proportional to its volume, but to the area of its boundary. Think of that for a moment. All the information needed to describe the entire three-dimensional interior of a region, every star, every planet, every person, could be entirely encoded on its two-dimensional surface, like a cosmic DVD. If this principle holds for the entire universe, it would mean that the true information content of our observable cosmos is not 10 to the 120, but a number derived from the area of its boundary, which is vastly smaller. The universe, in a sense, might be a projection, a hologram. The cosmological implications of this are staggering. If information is a fundamental currency of the cosmos, then the universe's evolution could be seen as a computation, a process of transforming and processing these bits. The laws of physics might not be laws about forces and fields, but about information processing rules. The initial low entropy state of the Big Bang would then represent a highly specific, information pure initial condition, and the subsequent expansion would be the execution of a cosmic program, generating complexity and information as it runs. This perspective could even offer a new way to understand dark energy. Perhaps the accelerating expansion isn't driven by a mysterious force, but is a consequence of the universe reaching its maximum information storage capacity. As space expands, it creates new volume, and with it, new potential for storing information. The acceleration could be the universe's way of making more memory available. Yet, the most profound question remains unanswered and perhaps unanswerable with our current knowledge. If the universe is indeed a vast informational structure, what, or who, is the programmer? Is the cosmic code simply running on its own, a self-contained, self-referential system that exists because it can? Or does the sheer existence of this complex, law-driven information suggest something else entirely? The mystery of the universe's information content forces us to confront the very nature of reality, blurring the line between the physical and the abstract, and suggesting that the ultimate truth of the cosmos might be written not in particles or forces, but in bits. These immense, seemingly empty regions between the threads of the cosmic web are not just passive blanks. They are active players in the evolution of the universe, and their origins and contents are a profound mystery. A cosmic void is far more than just a place where a few galaxies are missing. These are staggering deserts of space, some stretching over 350 million light-years across. To put that in perspective, if our Milky Way were the size of a grain of sand, crossing one of these voids would be like traveling the distance between New York and London. Within these caverns, the density of galaxies can be 10 to 100 times lower than the cosmic average. They are the universe's emptiest places, but emptiness in space is a relative term, and it's what might be hiding within that emptiness that fuels scientific debate. One of the leading theories for their formation is surprisingly straightforward, rooted in the very same gravitational processes that built the galaxies themselves. Imagine the early universe after the Big Bang, a nearly smooth soup of matter with tiny, quantum fluctuation ripples. Over billions of years, gravity acts as an amplifier. The slightly denser regions pull in more and more matter, growing into galaxies and the dense filaments of the cosmic web. Conversely, the slightly less dense regions get left behind. As matter flows out of these underdense areas and into the surrounding filaments, the voids expand and deepen. It's a gravitational landslide on a cosmic scale. In this view, voids are simply the inevitable and natural inverse of the clusters. They are the valleys carved out by the same forces that built the mountains. Their sheer size and emptiness are a direct result of this relentless drainage over eons. However, their profound emptiness has led to more exotic proposals. Could these voids be more than just evacuated regions? Could they be the primary reservoirs for the universe's most mysterious component, dark energy? We know dark energy is causing the expansion of the universe to accelerate, but we don't know if its strength is perfectly uniform everywhere. Some theories suggest that dark energy might be concentrated in these empty spaces. Think of it like this: if dark energy is a property of space itself, then where there is the most space, the most pure vacuum, its repulsive effect might be strongest. In this scenario, a void wouldn't just be expanding with the rest of the universe. It would be pushing itself apart from the inside, actively accelerating its own growth and contributing disproportionately to the overall expansion of the cosmos. The void becomes an engine of isolation, relentlessly pushing galaxies away from its center and ensuring its own emptiness. This idea connects to one of the most radical possibilities, that the physical constants themselves, like the strength of gravity or the speed of light, could be different inside a void. Our entire understanding of physics is built on observations within our own galactic neighborhood, a region of relatively average density. But what if the rules of the game change in these extreme low-density environments? This concept is related to theories of modified gravity, which propose that our understanding of gravity is incomplete and that it behaves differently where its pull is exceedingly weak. In the deep quiet of a void, where the gravitational field is almost negligible, perhaps a different set of physical laws takes over. It's a haunting thought that the fundamental rules of reality might not be universal, but could instead depend on your address within the cosmos, with the voids representing realms where the familiar laws of physics have simply gone quiet. Observing these voids directly is a monumental challenge precisely because they are so empty. Astronomers use them as natural laboratories in a unique way, by studying what isn't there. They meticulously map the distribution of galaxies to define the void's boundaries. Then, they use a phenomenon called gravitational lensing. Even though a void has very little mass, its immense volume means it still has a gravitational signature. It's a hill of negative gravity. When light from a distant galaxy passes through a void, its path is subtly altered, not by being pulled inward, but by being pushed outward slightly compared to the surrounding denser regions. By measuring this incredibly faint distortion, scientists can weigh the void, or more accurately, weigh the lack of matter within it. This helps distinguish between a void that is truly empty and one that might be filled with a smooth, undetected distribution of dark matter or dark energy. The largest of these voids, like the Boötes void, present their own special puzzles. Discovered in the 1980s, it was initially found to be so devoid of galaxies that it was nicknamed the Great Nothing. While later surveys found a few dozen galaxies scattered within its vast volume, its emptiness remains shocking. The existence of such a colossal void so early in the universe's history is difficult to explain through gravitational formation alone. It may point to an extraordinarily large initial underdensity in the primordial universe, a single massive quantum fluctuation that was stretched to an immense scale by inflation. These supervoids might be the fossil imprints of the rarest kinds of fluctuations from the birth of the cosmos, making them not just empty spaces, but unique windows into the very first moments of time. They stand as silent, expansive monuments to the randomness of creation, challenging us to understand whether their void is a simple absence or a space humming with different, hidden rules. Imagine finding a towering, ancient oak tree in a forest, and being told by a botanist that the forest itself is younger than the tree. It sounds impossible, a clear contradiction. Yet, this is precisely the kind of baffling puzzle astronomers face with the universe's age paradox. Our most precise measurements tell us the cosmos is 13.8 billion years old, a figure etched into the foundation of modern cosmology. But when we look out at the oldest stars in our own galaxy, some of them appear to be even older. This isn't a minor accounting error. It's a direct challenge to our cosmic timeline, suggesting a profound disconnect that could point to errors in our measurements, flaws in our models, or even a need to rethink how we measure time itself on the grandest scales. To understand the depth of this mystery, we need to look at how we date these ancient celestial objects. The universe's age is measured primarily through the cosmic microwave background. By analyzing the subtle fluctuations in this afterglow of the Big Bang, cosmologists can trace the expansion history of the universe backwards to time zero, arriving at that 13.8 billion year figure with remarkable precision. It's like calculating the age of a tree by measuring the expansion of its rings from the trunk outward. But the stars present a different challenge. To determine the age of a star, astronomers use a technique called stellar evolution modeling. They look at a star's brightness, its temperature, and most crucially, its chemical composition. Stars that formed very early in the universe's history are composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They contain virtually none of the heavier elements like iron or carbon, which were created later inside stars and spewed out by supernova. By identifying these metal-poor stars and then comparing their observed properties to sophisticated computer models of how stars burn their fuel over time, scientists can estimate their age. Some of the oldest stars in the Milky Way's halo, like the famous Methuselah star, have been given ages tantalizingly close to, or in some initial estimates even exceeding, the age of the universe itself. So, how do we resolve this impossible contradiction? The answer almost certainly lies in the margins of error and the complexities of both methods. For the stars, the uncertainty is in the models. Determining a star's age is not like reading a birth certificate. It's more like making an educated guess about a person's age based on their hairstyle, clothing, and a blurry photograph. The models rely on our understanding of complex physics, like the opacity of stellar material and the rate of nuclear fusion in the core. A small miscalibration in these factors can lead to an age estimate that is off by 1 billion years or more. For the Methuselah star, improved measurements of its distance and brightness using the Hubble Space Telescope, combined with better models that account for its precise mix of elements, have brought its estimated age down to about 14.5 billion years, plus or minus 800 million. This error bar now just barely overlaps with the age of the universe, making the paradox less severe but not entirely erased. It shows us how finer data can shrink the discrepancy, suggesting that the problem may ultimately be one of measurement precision rather than a fundamental flaw. However, the more thrilling possibility is that the paradox is real and points to a genuine error in our cosmological model. The 13.8 billion year age is not a standalone number. It is derived from a specific model of the universe's composition and expansion history, the lambda cold dark matter model. This model tells us how fast the universe has been expanding and what it is made of: normal matter, and dark energy. If any of these ingredients are wrong, the calculated age could be wrong. For instance, if the Hubble constant, the rate of the universe's current expansion, is higher than we think, as some local measurements suggest, it would imply a younger universe. A faster expanding universe would have taken less time to reach its current size. Alternatively, if our understanding of dark energy is incomplete, and it has changed over time in a way we haven't accounted for, that too could alter the cosmic age calculation. The age paradox could therefore be another manifestation of the Hubble tension, a collective sign that our standard model of cosmology, while incredibly successful, is missing a crucial piece of the puzzle. Beyond these explanations lies a truly mind-bending thought. Could the paradox be telling us something about the nature of time? Our entire chronology is built on the assumption that time has flowed at a constant, universal rate since the Big Bang. But what if that's not entirely true? According to Einstein's theory of general relativity, gravity warps time. A clock ticks slower in a stronger gravitational field. The cores of those ancient stars are places of immense gravity and pressure. Could the extreme conditions within them have affected the rate at which nuclear reactions proceeded, making them appear older from our external perspective? Furthermore, on a cosmic scale, the expansion of the universe itself defines the arrow of time. If our understanding of that expansion is even slightly off, our measure of cosmic time could be fundamentally skewed. The age paradox, therefore, is more than a conflict between two numbers. It is a profound reminder that our grasp on cosmic history is still evolving, and that the universe may yet have secrets about its own beginning that we are only beginning to uncover. And so we arrive at the final and perhaps most profound question of all, a mystery that has haunted philosophers and scientists for millennia and sits at the absolute limit of human comprehension. We've charted the observable universe, we've mapped the cosmic web, and we've peered back to the first light of the Big Bang. But we are inevitably drawn to the ultimate horizon. Does the universe, the totality of all that exists, have a boundary, or does it simply go on forever? This isn't just a question about more galaxies. It's a question about the very nature of reality, existence, and the meaning of nothingness itself. Let's first consider the possibility of a finite universe with a physical edge. Imagine, for a moment, that you could travel in a spaceship fast enough to eventually reach this boundary. What would you find? A cosmic wall, a great, impenetrable barrier beyond which there is nothing. But this idea of a literal edge immediately creates a paradox. If there is a boundary, then there must be something on the other side of it, even if that something is just empty space. But empty space, by its very definition, is still something. It is a volume, a part of the cosmos. The concept of a true, absolute nothing is almost impossible for our brains to conceive. We can say the words, but we cannot truly picture a state of non-existence, a complete absence of space, time, and physical laws. If the universe is all there is, then by definition, there cannot be an outside for it to be contained within. The very question, what is outside the universe, might be a linguistic trap, a nonsense question like asking what sound the color purple makes. This is where the multiverse hypothesis offers a breathtaking escape from this philosophical box. If our universe is just one bubble in a vast, perhaps infinite, cosmic foam of other universes, then the question of a boundary is transformed. The edge of our universe wouldn't be a wall into nothingness, but a transitional zone where the laws of physics as we know them break down and give way to the radically different laws of another bubble universe. In this view, the question isn't what's outside, but what's next door. The multiverse provides a kind of container, a larger meta-reality often called the quantum vacuum or the inflationary field, which can host an infinite number of universes, each with its own unique properties. This doesn't necessarily make the concept easier to grasp, but it replaces the unnerving idea of absolute nothingness with a perhaps more comforting, though infinitely stranger, concept of a greater, structured reality beyond our own. Yet, we must ask, is this even science? Can we ever test or falsify the idea of a multiverse? Many scientists argue that if these other universes are permanently beyond our causal horizon, forever separated from us by an insurmountable inflationary barrier, then the multiverse concept moves from physics into the realm of metaphysics. It becomes a beautiful, mathematically elegant story, but one that may never be subject to experimental verification. However, proponents counter that the theory of inflation, which predicts the multiverse, does make testable predictions about the universe we can see, like its flatness and the specific pattern of the cosmic microwave background. The shadow of the greater multiverse, they argue, is imprinted on our own local reality. Furthermore, if a neighboring universe ever collided with ours in the distant past, it might have left a bruise, a detectable imprint, on the CMB. A faint, circular pattern that would be the ultimate evidence we are not alone in the greater metacosmos. Ultimately, the mystery of the boundary of reality forces us to confront the limits of scientific inquiry itself. Science is built on observation and measurement, but we are asking a question about what, by its very definition, may be unobservable and immeasurable from our vantage point. The answer may not lie in building a bigger telescope, but in a revolution in our understanding of logic, mathematics, and the very meaning of existence. We are like fish in a pond, trying to comprehend the concept of dry. We can speculate, we can create models, but we may never truly know. And perhaps that is the most humbling and beautiful truth of all, that the universe, in its infinite majesty, retains a final, perfect secret, a mystery that defines the very boundary not just of space, but of human understanding. From the shattering silence of the Fermi paradox to the ghostly whisper of the cosmic neutrino background, from the impossible alignment of the axis of evil to the foundational crack of the Hubble tension, we have journeyed through 30 of the most profound mysteries that define the frontier of modern cosmology. Each one represents a crack in the facade of our understanding, a place where the map of reality turns blank, and the notation reads, "Here be dragons." We have stood at the particle horizon, the ultimate limit of what we can see, and asked what lies beyond in the unknowable dark. We have grappled with the true nature of the forces that shape our cosmic fate, the invisible grip of dark matter, and the repulsive phantom of dark energy. We have considered the possibility that our universe is not alone but one bubble in an infinite multiversal foam. And we have dared to ask what, if anything, came before the beginning of time itself. These are not merely academic puzzles to be solved and filed away. Every single unanswered question is a beacon, an invitation to a grander and more incredible reality. The fact that we do not have the answers is not a failure of science. It is its greatest triumph. It means the universe is still capable of surprising us, of reminding us that our journey of discovery has only just begun. Each mystery is an opportunity for a fundamental revolution in thought, a potential key that could unlock not just a new chapter in a textbook, but an entirely new way of perceiving existence. The discomfort of not knowing is the engine of all exploration, the very impulse that has driven us from ancient star charts to the James Webb Space Telescope. So as we conclude this tour of the cosmic edge, the greatest takeaway is not a list of facts, but an attitude, a sustained and joyful curiosity. The quest to understand the universe's deepest secrets is humanity's most epic story, a narrative written in mathematics and starlight, and it is a story in which every single one of us can play a part simply by looking up and wondering. The conversation does not end here, it starts here. We want to know which of these 30 mysteries captivates your imagination the most. Does the chilling silence of the Great Filter make you ponder our future? Does the infinite copycat paradox of a flat universe bend your mind? Or is it the quantum seed of all structure that you find most beautiful? Share your thoughts in the comments below. Let's continue this awe-inspiring discussion together, because the next great discovery might just begin with a spark of wonder from a curious mind like yours.